TensorFlow can do some amazing things when it comes to computer vision. In this course, machine learning engineer Noor Islam Mukhtari will teach you how to create multiple computer vision projects using TensorFlow 2.
Hello and welcome to my course, Introduction to TensorFlow for Computer Vision. So just a quick introduction about myself. My name is Noor Islam Mukhtari. I work as a machine learning engineer and I'll be your instructor for this course. If you have any questions regarding the course material and content or anything related to machine learning and computer vision, feel free to connect with me on LinkedIn and Twitter. And if you're starting a career in machine learning and computer vision, then please check out my free ML Job Ready checklist that I have put together, which contains some information that might help you to set a roadmap for things you should learn and maybe things that the machine learning and computer vision industries might expect from you. So all of these information regarding my social media accounts and also this free checklist can be found in the link below. It's one link, but it's going to show you all of the necessary information once you click it. Let's take a look at the course outline. So we're going to start the course by doing some software setup. Then I'm going to show you how to do image classification using MNIST dataset, which is basically the equivalent of the Hello World examples in the machine learning field. Then we're going to look at the image classification using German traffic signs, which is a real-world dataset that reflects more challenges compared to the MNIST dataset. So for the software setup, we're going to start by downloading and installing Visual Studio Code. I'm also going to show you how to get Miniconda. I'm going to tell you why we need it and how to install it. We're going to be using Miniconda with VS Code, so I'm going to show you how to make those two work together. Then we're going to install TensorFlow 2 CPU and GPU versions. We're also going to be installing different Python packages along the way. For the second part, which is the MNIST example, we're going to basically explore the MNIST dataset. I'm going to show you how to build a function that randomly looks into the dataset and it gives you some ideas about how this dataset is constructed. I'm also going to show you how to use TensorFlow layers, how to import them, and how to use them to build a neural network. We're going to be building the same neural network architecture in 3 different ways, which are the ways supported by TensorFlow. So the first one is called the sequential way, by using the sequential class. The second approach is called the functional way, which is basically your model is wrapped inside a function. And the third approach is the model class way, which is by inheriting from the model class. We then gonna do the compilation of the model and we're gonna fit the MNIST dataset into our model. We're gonna finish this part of the course by restructuring our code for better readability, which is something you're gonna find yourself often doing when working on machine learning projects in the industry. And for the last part of the course, we're gonna be working with the German traffic signs dataset, which is a real-world dataset that reflects the real challenges when working on machine learning projects compared to prepared datasets like the MNIST dataset. So for this, we're going to start by downloading and exploring the dataset. We're going to prepare the training, validation, and the test sets because they're not already prepared. We're going to build our neural network. We're going to create some data generators, which is a different approach than the one we will be using for the first example, which is the MNIST example. We're going to compile the model and fit the data. I'm also going to show you how to add some callbacks and why they could be very useful. And I'm going to show you how to evaluate your model using the generators you created before. And then I'm going to show you some potential improvements that you can do to get even better results. And we're going to finish this part of the course and basically the whole course by an example of how you would use your model to make prediction on single images. So basically how to build a standalone example that can make or that can use your model in order to make separate predictions. So who is this course for? Basically, this course is for anyone who's interested in learning about TensorFlow, specifically for computer vision applications. Ideally, you should have good knowledge about Python, like classes and functions in Python, and also basic concepts in deep learning, such as convolutional layers. So why would you learn TensorFlow anyway? Well, there are several reasons, but these are three of the main reasons in my opinion. So TensorFlow is the leading framework in deep learning, followed by PyTorch, and you can build powerful deep learning solutions with it for your own use and also for your company, the company you're working for. And there are lots of companies working on deep learning projects and they are using TensorFlow. So the job market is very large and it's only growing. So these are the main reasons of why you would want to learn TensorFlow. But at the end of the day, maybe you just want to learn it for fun. So that depends on you. So just a quick note before we continue with the course material. We will be using an IDE and not notebooks. We will be specifically using Visual Studio Code. And this is for several reasons. In industry projects, you usually use IDEs and not notebooks. With IDEs, you easily scale your machine learning code. So you can add a lot of scripts, you can test them separately, you can import them in different and other scripts. And also, I am for the opinion that says that IDEs are for building your projects and notebooks are for presenting your work. So for me, and I think many other machine learning practitioners agree with me on this, is that we usually use notebooks for presenting the work, but when we're building large machine learning projects, we usually go with IDEs. So the first thing we're going to start doing is downloading Visual Studio Code. It's an IDE that we will be using throughout the course to write the code and also to run that code. So if you go to code.visualstudio.com, you're going to get this page here. And as you can see, it automatically detected my system. So I can just click here and download Visual Studio Code for my Windows machine. If you have a different machine, it should detect it. If not, then you can just click on this button here and choose the right software for your machine. So if you click this, you're just going to get this download here and you can just save it to your machine and run this executable just like you would run on any other installation process. There's nothing unique or special here, so I'm not going to go through it here. Now, after we install it, if you go to your run menu here and you just type Visual Studio Code, you're gonna get this the icon here where you can run Visual Studio Code. Usually I like to pin it to my start, so as you can see it's already pinned here, which means I can just access it from here. You can choose to do that as well if you prefer that. So let's run Visual Studio Code. And the first time you run it, you're going to get this new window here where you have the starting menu. So you can create a new file, open a file, or do all of these other things. And also for me, as you can see, I have this part here that says recent, which are my recent projects. If it's the first time you're using Visual Studio Code, you will not have this. So the first thing I'm going to do is just to open a folder. So I'm going to click on open a folder. Here you can choose any place on your machine to open that folder. So for me, I have chosen this place on my machine. So I have a disk called D, Code for Courses and Introduction to TensorFlow 2. I created this new folder and now I'm just going to select it. So select folder. And now it's going to open this new window. Okay, here it says if I trust the authors of these files. Yes, no problem. These are my files. So here you get this new window where you have this empty folder on the left, and you can add new files. You can also add new folders inside of this folder. And here we will get the place where we can write code, and also we can get the terminal at the bottom here. So for now, this is it for installing and setting up Visual Studio Code. What we're going to do now is look at the other software that we will use throughout the course. And also later, we're going to start adding files here so that we can start writing some code. So the second software we need to install is called Miniconda. So if you look online, you're going to find two types of products for Conda. There's Miniconda and there's Anaconda. Anaconda is actually a GUI that allows you to do almost everything that Miniconda allows you to do. The only difference is that Miniconda does not have a GUI. We will just use it in a command line prompt. So if you type Miniconda in your Google search bar, you're going to get the first result here. So if we just open this, here you get all of these links to install Miniconda on your machine. So if you are on Windows, you choose this. Otherwise, you choose the other types here. And again, there's nothing special here. You can just click the link, save the file to your local machine, and then run the installation process. And also, there's nothing special when installing Miniconda, so I'm not gonna go through it here. Now, when you install Miniconda, if you go to your run menu here and you just type Miniconda, you're gonna see Anaconda prompt, and between parentheses there's Miniconda 3. So if you open it, you're gonna see that it looks just like the command window on Windows. So they are basically or almost identical. The only difference that we can notice here is that here we see this name called base between parentheses here, and here we can see it in the default Windows command line window. Now, what this means is that, in fact, in the Miniconda prompt, we are actually now inside what's called a virtual environment, and this virtual environment is called base. So I'll go a little bit into more details about what these virtual environments do and why would we need them, and why don't we just install things straight on our system using just the Windows command line prompt. I'll go into details about this just next. So what are these virtual environments? Well, you can actually think of them as these separate entities inside your system, but they do not necessarily affect your system. So, for example, we can think of it in this way. So you have your system, and inside your system you have Python, let's say 3.8 installed, and you have some Python packages. And now with virtual environments, what we can do is create as many environments as we want. So for example, here I show you an example where we created 3 different virtual environments. So the first one is called VM1, the second one VM2, and we have VM3. So in the first one, we can install Python 3.7, and for example, we install TensorFlow 2.6. Now, when you do this, you're not actually installing Python or the Python packages straight onto your system. You're actually installing them inside this virtual environment. So this virtual environment, it actually lives inside your system, but what you install in it does not necessarily affect your system. So here, as you can see on your system, you might have Python version 3.8, but inside your virtual environment, you can change that and you can use Python 3.7. And as you can see, you can create as many virtual environments as you like. And the goal here, or the why would you even want to do something like this, is really when you're doing machine learning or data science, you're going to be doing lots of experimentation. So, for example, there might be a new TensorFlow version that has some new functionalities and you want to test it. If you have everything installed on your system and then you just upgrade to the newest version of TensorFlow, then you might affect your existing code. So you might, something that has already worked in the previous version of TensorFlow might not work in the newest version, and that could cause a lot of conflicts. So now you find yourself in a situation where you have to go back to an older version, which is not very good. So when you do this, you can do these experimentations separately. And as you can see, for example, if I want to test PyTorch and I don't want it to be used in the same virtual environment as TensorFlow, I can create a completely separate virtual environment, install whatever version of Python I need, and then I install PyTorch here. And if I want to test, for example, an older version of PyTorch, I can create another virtual environment and do the same thing. And you can imagine all of these benefits that you can have. For example, many companies are still using TensorFlow version 1.x. So if you want to do this, if you want to install a previous version or an older version of TensorFlow, so 1.5, 1.6, then it's better to install it in a virtual environment instead of doing it on your system. So this is the goal of why we're trying to use virtual environments. I really encourage you to use this kind of framework when you're doing your experimentation instead of installing everything on your system. I've been working in the machine learning field for some years now, and I have always found that it's better to use virtual environments rather than install everything on your directly on your system. So I hope that now you can see the benefits of following this kind of paradigm. And next, let's start creating a virtual environment and install necessary Python and Python packages inside of it. So now, just before we start installing TensorFlow and creating our virtual environment, let me just clear some of the doubt that you might have here. So as you can see, when we installed Miniconda, we have this command prompt here, and also I showed you that we have the default Windows command line here, and they are similar. So, but how are we going to use our virtual environments inside Visual Studio Code? So in fact, if you go to Visual Studio Code, if you go to Terminal, New Terminal, here, in fact, we are inside our command line, default command line window. So what you do here is going to be identical to what you would do here. And in fact, let's just, for example, type Python. So here you see on my system, there's Python 3.6.8 installed. And here, if I write Python, I get the same version here. So I have whatever I do here, I'll be able to do it here and vice versa. And now let me just exit this. What we want is to actually be able to use our virtual environments and just use Miniconda in general inside our terminal here on Visual Studio Code. So in order to do that, what you can do is just look up where Miniconda is installed on your machine. So for me, I'm using a tool called Everything. It's a search tool. You don't have to install it. I just prefer it than the default search tool on Windows. So here, when I type Miniconda 3, which is the software that we installed, if I open this folder here, there is another folder called scripts, and then there is activate.bat. So if I just take this, copy it, paste it, and then run activate.bat. Now, as you can see, I have the base name here written before my before this path here, and as you can see, we have the same thing here. So now we are in fact inside the virtual environment called base, and whatever you do inside this command, this window here, is going to be reflected here and vice versa. So now that we can access conda commands on our Visual Studio Code terminal, let's try to see what we can do with it. So here, let me just clear this part here. And in fact, you can run so many conda commands. So to run the conda command, you start by writing conda, and then you finish the rest of the command with whatever you need to do. So for example, we can look at our virtual environments that are already installed. In order to do that, you can run this command, conda info --amps. And if you've never had Miniconda before, you will have nothing when you run this command. But for me, as you can see, I already have some virtual environments installed here. So let me just clear this one here. And next, what we're going to do is create a new virtual environment, and then we will choose the right Python version that we want, and then we're going to install TensorFlow inside that virtual environment. To create a virtual environment using conda, the command that you should run is conda create -n. Now you can give a name to your virtual environment. You can choose any name you like. Usually, for me, since I do many experimentations with TensorFlow, I just like to call it, for example, TF2, or I give it the full, for example, version of TensorFlow, so TF2.5 or 0.6 or whatever. And here, let's just call it, for example, TF2 VM. So VM for virtual environment. And then you can give it the parameter Python. And here you can choose whatever version of Python you like. So let's just use 3.8, since I've been working with it for a long time, and it works great with TensorFlow. So here I'm just gonna run this command. So now it's gonna ask us whether we accept to install these necessary packages. So I'm gonna choose yes and click. And this should not take that long because these are not large packages. So after we have our packages installed, we can run conda activate tf2 venv. And of course, you can see that the suggestion is shown here in order to activate your virtual environment. So now, if you remember, we are inside a virtual environment called base. So after I run this command, now we're inside our newly created virtual environment called TF2 VM. And here, whatever you install is going to be separate from your system, so it will not affect it. So here, for example, let's just run Python. And as you can see, it's version 3.8. If you remember, on my system, I have 3.6 installed, but here inside my virtual environment, because I specified that I want a Python version 3.8, I have 3.8 installed here. So now that we have created our virtual environment, we can start installing the necessary packages. So now we can install, for example, TensorFlow. And if you go to the official website of TensorFlow, you can see, if you just go to tensorflow.org/install, you can see different ways you can install TensorFlow. For us, we're going to use TensorFlow, or download it and install it as a Python package. So these are the commands we can run. So here, first command we can run is just for upgrading pip. So if you don't know what pip is, so pip is just a package manager that helps us install Python packages. So let me paste it here and see if I don't have the latest version. Apparently not. So it's just gonna download it and install it. So when I tried to upgrade pip on my machine, it gave me a basically an access error. But if you have that error, you can just run the same command, but you add -- user at the end. So for me, it says requirement already satisfied. In fact, I didn't really need to run this command. I already had the last version of pip already installed, but you can run it just for the sake of it. And now we're gonna use this command, so pip install TensorFlow. And here I just want to mention something really quickly. As you can see, it mentions that the current stable release for CPU and GPU. So when you run this command, it's gonna install the stable versions for both CPU and GPU support. I can't remember before which release from TensorFlow, but before, in order to install the GPU version, you would add TensorFlow-GPU. So you specifically mentioned that you want to install TensorFlow with GPU support, but apparently now when you just run this command, it's gonna install the stable release for CPU and GPU. So I'm gonna go back to my virtual environment here. I'm just gonna paste it, pip install TensorFlow, and let's run this command. Again, just to mention this important point, whatever we're installing here is being installed inside our virtual environment and not inside our system. So this might take a little time depending on your internet speed and on your system. So when the download and installation is finished, I'll be back to show you what we can do next. So now I have TensorFlow downloaded and installed inside my virtual environment, and I can verify that, for example, by running Python console here and just trying to import TensorFlow, and it should be imported without any problems. And just to show you that we're actually not installing things inside our on our system directly, here if I run Python and I do import TensorFlow, you see that module name or module not found error. So it doesn't find the TensorFlow module because it's not installed on my system. I'm just showing you this here because from time to time you might face a problem like this and you start asking yourself, why don't I have TensorFlow when you have already installed it? But just make sure that if you install it in one specific virtual environment, you should be using that virtual environment to run your code. And this small detail here could help you solve this kind of errors. And now that we have it, what I would like to do is just run a command tensorflow.config.list physical devices. So what this command is going to do is to show me on my machine which devices can I use to train deep learning models using TensorFlow. So as you can see here, I have two devices. There is the CPU and there is the GPU. There's only one GPU, as you can see. For you, it's very likely, if it's the first time you're using TensorFlow, it's very likely that you will not have this second part here. You won't have the GPU. And this could be for several reasons. For example, you may not have an NVIDIA GPU on your machine, so that's a common reason why you wouldn't have this. The second common reason is that you might have an NVIDIA GPU, but it doesn't have support for training TensorFlow or deep learning models in general on that GPU. And if you're not in one of these two categories, then most likely you're not seeing the GPU because you just haven't set up what's necessary in order for you to run the training on the GPU. And for me, I have already done the necessary setup, and I do have an NVIDIA GPU that can run the training. That's why I'm seeing it here. For you, if you don't fall in the first two categories and you know that you can run the training on your GPU, then I'll show you next what are the necessary hardware requirements and software requirements. What are the things that you need to install in order to be able to use your GPU? If you want to be able to run the training on your GPU and you know that you have an NVIDIA GPU, one thing you can do is to follow the right process that's mentioned in the official TensorFlow installation page. So here, if you go to the download package, which is what we just used, if you go to GPU guide, you can open this page here. And when you use a pip package like we're doing, you need to have some hardware requirements and also software requirements. So the first thing, let's check the hardware requirements. So as you can see here, it mentions that there are some NVIDIA cards where you can that are supported for you to train deep learning models on them. So if you open this list here of cards that have CUDA enabled architectures, you can see a list of devices here, and you can try to find whether your device is inside this list or not. So in fact, funnily enough, for me, I actually have a card GeForce GTX 1050 Ti, and it doesn't exist on this list, but I still can run the training on it anyway. I remember the first time when I checked the list, I didn't find it. Then I just started searching online. I found that many people said yes, they have the same card and they were able to run the training on it. So this is just a small remark. But if you find your card here, then you can definitely run the training on the GPU. So that's the first thing you need to check. If you have that, then most likely you can run the training, and then you have some remarks mentioned here. For example, for GPUs with unsupported CUDA architectures, or to avoid JIT compilation, use different versions of NVIDIA. So you can check these if you fall into one of these categories. But for me, usually just checking whether the architecture works is enough. And then for the software requirements, this is where, in fact, you need to have some software installed before your NVIDIA card can recognize that you can do the training using TensorFlow. So the first thing is the NVIDIA GPU drivers. So here it says CUDA 11.2 requires 450 or higher. So you can go to the website here, and for me it has automatically detected. In fact, I think that it's because I have already done this, so maybe it's saved in my in the cookies. But for you, if you don't see your machine directly here, you can just go search for it manually. So you choose the product type, the product series, and then at the end you just click search, and it's going to give you the download link. And again, this is when you download this and you start installing it. Okay, it didn't start automatically. Let me click again. Okay, now when you have this on your machine, you just run the installation process. There's nothing really special. You just go next, 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 and you install everything. So that's the first thing that you need to do. And then you have CUDA toolkits that you need to install. And just I want to mention something here, because I think a lot of people make a mistake when they start installing all of this software. So here specifically it mentions, for example, CUDA 11.2, and also TensorFlow supports CUDA 11.2. So any version of TensorFlow that's higher than 2.5, it requires CUDA 11.2. So for us, we have installed TensorFlow. So if I do, for example, TensorFlow, and then I just run or check the version of TensorFlow version. So here you can see I have version 2.6.0. So I do fall into this category. I need to have CUDA 11.2 installed. Here, when you go to the CUDA Toolkit archive, you just don't take the latest version. For example, I see many people do this mistake. They just go to the latest version. But here, if it's mentioned that you need to use 11.2, then you need to look for 11.2. And here, what I usually do is I take the latest version of 11.2, because here you can see there's 11.2.0, 0.1, 0.2. So I just take this one here. And then you just choose your operating system. The architecture is only one here, version 10 of Windows. And then you can choose one of two options. There is the local installer and the network installer. The difference is that the local installer is a large file, which doesn't require internet access. I mean, after you download it, you don't require internet access in order to install CUDA Toolkit. And this one is a smaller file, but it does require internet access. If you have good internet, then I suggest you just download this small file. If not, then you can download the largest file here. And again, there's nothing really special about this. You just download it and then you go next. And then you have the CUDA Toolkit installed on your machine. So that's the second part. For the kubtai, you don't need to do that. It mentions here that it ships with CUDA Toolkit. So if you have the CUDA Toolkit, you already have kubtai. And then you need to install cuDNN SDK 8.1.0. So if we click this, let me check here. So download cuDNN. And in fact, for you to download that file or that folder, you need to be a member on the website. And you can do this for free. You can just log in if you already have an account, or you can join now, for example, and you just use your email, and there is nothing special here. You just join the website. So for me, I already have an account here. So once I log into my account, I get this web page here. So I'm just gonna agree to the terms, and then here you can download the version for or cuDNN 8.2.4. And in fact, here, when you look at this, you see that there is for CUDA 11.4 and there is for CUDA 11.2. Let's see if we can find for CUDA 11.2. So there is none. In that case, we're just gonna use the latest version here. So let me just go back here and check. Okay, we have the CUDA versions. Yes, apparently. Okay, 11.1 here. Yeah, in fact, there is. So this is sometimes a problem that many people face. So here we need cuDNN SDK 8.1.0. When I clicked on the cuDNN versions, I get to this website here. And here, if you just don't take the latest version, you need to look for your own specific version. So here I have the version 8.1.0, which is what we need. So for 8.1.0, we have one for CUDA 10.2 and then one for CUDA 11.0.1 and 0.2. For us, we have CUDA 11.2, as you remember. So we need this version here. So these are small details, but just make sure you follow them so that you don't face a problem later. Many times I find people saying that they installed everything, but still their card does not recognize, cannot do the training with TensorFlow. but usually the problem just comes from one of these small details. So if you click this, then you can choose the right software for your machine. So for example, we are on a Windows machine, so I can just click cuDNN library for Windows. And this is going to download a zipped folder. And in fact, I already have it on my machine here. Now I'm going to show you what you need to do with this folder. So when you installed CUDA 11.2, it was installed in this path here. So if you go to C, Program Files, NVIDIA GPU Computing Toolkit, then you go to CUDA. For me, I have several versions of CUDA because from time to time I would upgrade or use the newest version of TensorFlow, and then many times it requires new version of CUDA, so I would download and install the right CUDA version. For you, if you've never did this before, then probably you will have only one version, which is 11.2. And now what we're gonna do with the zipped folder that you downloaded, what you need to do is to unzip it. So when you unzip it, you're gonna get a folder called CUDA. Inside of it, you're gonna have these folders and this file here. So what we're gonna do now is basically just copy the contents from these folders to the corresponding folders in CUDA 11.2. So for example, you would go to the bin folder, copy everything, then go here and paste everything. For me, I've already copied and pasted these, so I'm not gonna do it, but this is the only thing you need to do. Then you go to the include folder, copy everything, paste it in the include folder, and last you go to the lib folder, you copy everything inside x64, and then the same thing here, lib, you go to x64, and then you paste everything there. When you do this, you can go back to your terminal. So what I would suggest is to close and reopen the terminal. And then if you run the same command that that I showed you before, so for example, let's just do it again. Import TensorFlow. So here, if we run TensorFlow.list or config.list physical devices. Now you should be able to see this GPU part here. So now I have shown you exactly the full process of installing TensorFlow so that you can use it with your GPU if you have a CUDA enabled NVIDIA GPU. And this is gonna allow you to run the training of your deep learning models much faster, which is almost always recommended. And with this, let's now look at what we can start adding from the coding part so that we can start exploring TensorFlow library. So here we're going to start with the first classification task using TensorFlow, and it's actually a classical task. So basically what we want to achieve is to build a system that can take images like this one here or here or here, and at the output it would tell us whether there is a 3 or there is a 7, there is a 0 inside that image. So our data set looks something like this. Of course, think of these are as separate small images, just like these ones here. These are just put together here for visualizations purposes. So our data set has so many zeros, so many ones, twos until the digit 9. And we want to build a system that can take an image like this at the start or as an input, and at the output we want to get the value that's written inside of that that image. So it's always good to really think about whatever task you're trying to achieve before you start the coding part. So here, this is just a quick overview of what we want to achieve. And in fact, this MNIST task is you can say as a tradition in the deep learning community. It's just like a hello world program when you're learning a new programming language. So now that you have hopefully understood the purpose of this task, let's get into the code and see how we can achieve this goal here. Now let's get to the coding part. So the first thing I'm gonna do is just add a new file. I'm gonna call it, for example, MNIST example.py, and it's automatically opened on this side here. So let's start by importing, for example, TensorFlow, since we will definitely need it later. And one thing we gonna add from the start is just check if name equals main, then we're gonna run the code. So if you're not familiar with this Python part here, it just means that if I run my script, then I want this part here to be ran. And if I import it, for example, I can import my file into another script, then in that case, this part will not be called. It's a good habit to always add this when on your scripts when you want to separate the behaviors between importing those scripts and running those scripts. So the first thing that you might notice here is that it says TensorFlow is not accessed. It doesn't find TensorFlow. So here, in fact, what's happening is that if you run your script from the terminal, then there will be no problem. So if I do Python MNIST nothing is going to happen, but there will be no problem. That's what I mean. But here, if you try to run it using the run button here, then you see it says no module named TensorFlow. And in fact, what just happened is that VS Code has opened a new terminal window automatically, and it tried to run this script using our Python that exists on our system and not inside our virtual environment. So in fact, we still have our virtual environment here, and this is the new terminal window that was started by VS Code. So in order to run your scripts, so you can in fact just ignore these warnings here, and you just run your script from the terminal. But if this is annoying for you, as it is for me, you can fix it by actually telling VS Code that this code here that we're writing is going to be ran inside our virtual environment TF2VM. So in order to do that, you can click Control-Shift-P on your keyboard. So again, Control-Shift-P, you push them, you click them together, and then you just search for interpreter and you choose Python select interpreter. And here it's going to give you a list of different Python executables that it found on your system. And here we're going to look for the virtual environment that we created. So it's called TF2VM. So let's just go step by step here, try to find it. So I have many virtual environments. That's why it's not clear. Okay, it's this one. For you, you may not have all of these virtual environments, so it will be quick to spot which one is the environment that you created. So I'm going to click on TF2VM. And now, as you can see, VS Code recognizes TensorFlow because it's installed inside our virtual environment. And I can click this one here. And as you can see, the program runs correctly with no problem. So now let's go to our code editor here, and let's start looking into what we can do for our task that we defined previously. So one thing we can start doing is by actually importing the dataset. So in fact, if you're doing a new project with your own dataset, it may not be this easy, but since this is the first example or the first tutorial we're gonna do, we're just gonna use the easiest and the quickest things so that we can put something together and see basically the workflow of a TensorFlow program. So what we're gonna do is use TensorFlow.keras.datasets, or let me just check. Yes, in fact, it should be datasets.load or .MNIST.load data. So let me just do this. And in fact, what this is going to do is load our data, but we need to tell it where to store it. So for us, we're just going to use xtrain for the training data set and ytrain for the corresponding labels. And then we're going to use xtest and ytest. So what this is going to do is load the MNIST dataset. In fact, if it doesn't exist on your system, if it's the first time you'll be running this program here, then it will download it first, and then it's gonna load it into these variables that we defined here. And it's already split into two parts, one for training and one for testing. So let's run this command or this program here, and I would like to print the shapes of these variables that we defined and that we're gonna load our data set in them. So xtrain dot shape. Let me just run this, and I'm just gonna paste this 3 times, and I want to do this for every variable that we have here. Control C, Control V. So now let me just run my script again from the terminal, and let's see what we get. So as you can see, it has loaded the dataset and it has put them into these variables, and we can see the shapes or basically the size of the dataset. So as you can see, for the training part, there are 60,000 images. Each image is of 28 by 28 pixels. The labels, there are 60,000 labels because each image has its own label. And by the label here, I mean that if an image contains the number 3 in it, then the label will be the number 3. And for the test part, we have 10,000 images, and of course, their corresponding 10,000 labels. So just quickly to go through why do we separate our dataset into these two parts. So in fact, in deep learning, what we do is we do some sort of cross-validation. There are many types of cross-validation. The simplest one is to split the dataset into two parts. One you're going to use to train your model, and one you're going to use to validate your model. And the difference is that during the training, these are the examples that will be used. And at the end of each epoch, what's going to happen is that the neural network is going to run one forward pass of these test examples. And this is going to give you an idea of how your neural network is performing on data that's not used during the training. So this is going to give you an idea of how well the network is learning. So this is just, you can keep it in mind. There's a whole theory behind this, but I just want to go quickly through this so that you understand why do we have these two different splits. So now what is usually good to do is to explore more your dataset. So what we have done here is some sort of an exploration. We basically check the size of our dataset. We now know that each image is 28 by 28 pixels, but it's also good to plot some of the examples and their corresponding labels. So for that, I'm just gonna create a helping function. So I'm gonna call it, for example, display some examples, and what's going to take as parameters are the examples or data points and the labels. So basically what I want to do here is create a figure and add many of the images randomly. I'll choose them randomly from the dataset, and then I'll add them inside this figure, and then I'm going to plot this figure so that we can see those images. So one thing you can use, which is a very famous package in Python, is matplotlib. So usually we just call it PLT for short, and in order to do that, you need to import matplotlib.pyplot as PLT. And then you can use this package to do all sorts of things like creating figures and adding different images on those figures. So as you can see here, Visual Studio Code does not recognize this package here because, in fact, we don't have it installed inside our virtual machine. So before we go anywhere, let's just install it. And to install any new package, you can just run pip install and the name of the package, so matplotlib. And usually I install packages on the go, so whenever I need a package, I install it. I don't like to install many things in the beginning because I don't know beforehand which of the packages I'll definitely need and which ones I won't need. So usually I just write my code, and whenever I need a package, I install it on the spot. So here, let me run pip install matplotlib. So it shouldn't take long. Okay, it's installed, and now it should be recognized. I guess maybe it's not refreshed automatically, but now we can use PLT. So we're going to start by creating a figure, and we're going to give it a fig size of, let's say, 10 by 10. And then what we're going to do is basically plot 25 images. So it's going to be a grid of 5 by 5. So we're going to do a for loop. So for I in range 25. So I'm choosing 25 here. You can choose whatever number you like. For me, I think 25 images is already enough to get an idea about your dataset. And here, the first thing I'm going to do is randomly choose. So each time I'm going to randomly choose an index from my data set. So let me just code it, and it's going to be much clearer. So I'm going to do index and numpy. Okay, I don't have numpy imported, so let me just import numpy smp, and here I'm just gonna do np.random.randint. So I want to randomly choose an integer, and I really like this kind of a tooltip that comes when you're coding on Visual Studio Code, and it basically gives you a small documentation about that function and what you can do with it. So here, for this function, we need to give it a lower end and a higher end, and it's going to use an integer between those two numbers. So here I'm going to choose something between 0 and the size of, so examples.shape, and I'm going to do 0, and here -1. So what am I doing here? So if you remember here, whether you choose the training set or the test set, for example, the training set, there is 60,000 images. So I want to choose a number between 0 and basically 59,999, because that would represent the number corresponding to the last image. And here, this is all I'm doing. So here, I'm basically choosing between 0 and 60,000 minus 1. And then what I'm going to do is use this index to get the corresponding image. So now I can do examples index. And then I want to get also the corresponding label. So I'm going to do labels and index. And now I'm going to plot that specific image. So for that, I'm going to use PLT subplot. And just make sure, I think there is subplot and subplots, but what you want to use is subplot without the S. And here we gonna give it basically the grid size. So it's a 5 by 5 because we want to plot 25 images. And here, this is the number of the image. And here I'm gonna do plot. I'm gonna first plot the title. So the title of each image, I want it to be the corresponding label. So, and it also needs to be a string, sorry. So here I'm just gonna transform my label into a string. So this is going to be the title of each image. And then I'm gonna add an imshow method to show the corresponding image. So here I'm gonna do show my image. And at the end, you need to tell Python that show all of the figure now. So now that we have this function coded, let's try it out here by calling the name of the function. Then let's run it on the train set. So here, I'm gonna run it on the X train and Y train. So let me clear the terminal quickly and do Python MNIST example.py. So now, as you can see, we get these images in a 5 by 5 grid, and we have all of these examples. Now, one thing you might observe is that we have these images that have this kind of weird color, and also we have basically the space between the images is too small, so we don't clearly see that, okay, this has a label of 9, but it's not very clear. So let's fix these two problems quickly now. So first of all, we know that our images are grayscale images. They're not RGB images. Because here we see that the size is 28 by 28, which means there's only one channel, and there aren't 3 channels, so it's not an RGB image. So in order to tell Matplotlib that this is a grayscale image, we can use the CMap argument here, and we can tell it that it's actually gray. And to fix the problem of the layouts, what we can do is use plt.tight_layout, and this is gonna automatically add more space so that we can see the labels and the images in a much more understandable way. So let me run the command again, Python MNIST example.py. And as you can see now, it looks much more clear. These are the images that exist inside our dataset. They are grayscale images, and above each one we have the corresponding label. So this is a 2, this is a 1, this is a 4, a 3 here, a 6. So we have all of these examples. And why do we do this? It's just a way to basically quickly check your dataset. Sometimes what happens is that when you're building your own dataset, and you do this kind of exploration, you quickly spot some things. So for example, you might spot that this is a 0, but it's not labeled correctly. For example, you might see that this is labeled as 9 when it's actually a 0. So that's gonna give you basically just a quick hint that there are problems with your data set, and you can maybe go fix them quickly. And the good thing is that whenever you run this script, it's gonna choose randomly different images, so you can see different parts of your data set each time you run the script. So here we have the 261, for example, in the beginning, just so that we can remember. And let's run it again. Okay. And now, as you can see, we have 572 instead of the 261, I think it was before. So this is just about the exploration of your dataset. As I mentioned, it's always a good idea to do these quick exploration steps before you start doing anything. And now that we see that, okay, our dataset is more or less okay, let's see what we can do next in regards of creating a model and later training it. Now that we have our dataset loaded and ready, let's see how we can build our neural network. So, in fact, TensorFlow gives you access to so many layers that you can use to build your neural network. So if, for example, you do from TensorFlow.keras.layers import, here you have many different layers that you can import. For our classification task and for many of the computer vision tasks, we usually have a set of layers that we basically always use. So these layers are conv2D. So this is a 2D convolution. We also always use, of course, an input layer. So here I'm gonna add input. So this is a layer that basically gets our input and then passes it to the rest of the layers. And there is also the dense layer. So it's also called fully connected layer. We have the maxpool 2D. So since we're doing 2D convolutions, we're gonna combine them with maxpool 2D. And it's always good to use batch normalization to normalize our batches. And also, we might want to use a flatten layer, which basically takes the output from some multi-dimensional layers like a convolutional layer, and then it just flattens them and puts them in some sort of vector. And also, in fact, in many cases, you can use just global average pooling or global global average pool 2D. So this layer also can work in a way that's closely similar with flatten, but they're different in the way they do it. So flatten basically takes all of the outputs of a previous layer, puts them into a vector, but in the global average pooling, there is some sort of a computation of the mean based on some axes, and then the output usually is much smaller than the output given by a flattened layer. So here I'm basically mentioning some of the basic layers that we use in a neural network for doing image processing or doing deep learning for images type of things. So for classification, this is one case. There's also object detection, image segmentation. All of these tasks, usually you're going to find this type of layers in them. And sometimes you find more complex layers. And sometimes those complex layers are just basically stacking together different basic layers like these ones here. So These are the layers that we're going to use to build our neural network. And now let's see how we can build that neural network. There are several ways, mainly 3 ways that you can build a neural network in TensorFlow. We're going to explore them now one by one. The 3 approaches that TensorFlow gives us or provides us in order to be able to build deep learning models are the following. So the first approach is by using TensorFlow.keras.sequential. So you can call it the sequential way. This is the easiest way to build a deep learning model. You just stack different layers together, and we're gonna do this in a minute. The second approach is by what's called the functional way, or the functional approach. So basically here you build a function that returns a deep learning model, or let's just write a model. And the third approach is to basically inherit from a base class. This base class is in TensorFlow.keras.model. So you inherit from this class, and then you re-implement or you override some of the methods of this class, and then you can have a deep learning model. So inherit from this class. So these are the 3 different approaches. Let's start with the first one. So in order to build a deep learning model architecture using this sequential class, in fact, it's very easy. You just call, for example, let's call our model, and then you call this sequential class, and then you can start stacking layers here. So what we start with always is an input layer. So here we're going to use the input layer that we imported here. And what this input layer takes as an argument, it takes many arguments, but the main one that we need to set is the shape of the input. So as you remember, our images are 28 by 28, and they only have one channel. They are grayscale images, so there's only one channel. This means that our input needs to be 28 by 28 by 1. 1 represents only one channel. And then the second layer that we're going to add here is going to take as input this layer. And usually when you're doing image classification tasks or other computer vision related tasks in deep learning, you take the image and then you pass it through some convolutional layers. So here we're going to do the same thing. So conv2D. And since this is the first convolutional layer, let's go through some of the parameters that exist in this layer. So one thing that I like to do is to just hold the control key and then hover over that class. And as you can see, Visual Studio Code can give you so many information about that class. And here the mandatory parameters that we need to set are filters and the kernel size. And then you have the rest of the parameters already set. You can change them if you like. And here it even gives you some examples, and it gives some explanations of the different parameters. So the number of filters here, so let's start with, for example, 32 filters of size 3 by 3. And here let's also set an activation function, and I'm going to use a RealU activation function. So here there are all of these parameters. What do they basically represent for us? So this number here, the 32, represents how many filters or how many each filter has a set of weights. And in fact, here we're defining how many weights values are in that filter. So this means that we're creating 32 filters. Each filter is 3 by 3 of size. And then we're choosing an activation function here. We're choosing rectified linear unit. There are several activation functions. And all of these parameters, you might be thinking, why do we choose 32 and not another one? Why do we choose 3 by 3? And this is real U. Why do we choose these specific parameters? Where in fact, these parameters are hyperparameters. You might have heard of this term. And these are parameters that you can change, and each time you change and you train your new deep learning model and you see whether the accuracy has improved or not. So far there's no very solid theory on how many parameters you should choose in each phase. So it's really an experimental approach. You choose some of these parameters, you train your model, and then you go change them again and train your model again and see if you get a better accuracy. Now, I am choosing some of these parameters based on much previous work that has been done by researchers. If you see a lot of the neural networks used for classification, they would start with something very similar to this. So I am following on their footsteps because I know that they have done so many experimentations with those neural networks. So here I'm going to start with a convolutional layer. Usually what we do is we create a block of convolution where you have a convolutional layer, then you would use maxpool 2D, and then you use a batch normalization layer. And then you can do the same thing again, another convolution, maxpool normalization, and you just change, for example, the number of filters or the filter size here, or the activation function. So what this maxpool 2D does is that it takes the output of the convolution and it looks in both directions, and based on the pool size. So again, let's maybe go to the documentation that's written inside the code here. What you have is, let me just go way down. You have the pool size and it's 2 by 2. What this means is that the output of the convolution, we're going to look at 2 by 2 window of the output of this layer, and each time we're going to keep only the max value between those 4 values, because it's a 2 by 2 window, so there are 4 values. We only keep the max value between all of those 4 values. And here you can in fact change this. You can set the pool size to 4 by 4, which means it's a 4 by 4 window where you keep only the max value in that window. And again, why do we keep 2 by 2? Why don't we change it? As these are also hyperparameters that you can change, and each time you change, you retrain your model and see whether you get better results. So this also goes into that experimentation approach that we do as machine learning engineers or data scientists. So this is one way to do things, and in fact, you're not, let's say, you don't strictly need to follow these approaches. You can experiment. For example, you can add a convolution to the here, and you, for example, let's do 64 and 3 by 3 and activation is it activations or activations? Sorry, let me just check again. So here, let me go into the parameters. Activation, no, it's without an S. Okay. So you can do this, you can remove it, you can add another layer. Feel free to experiment with this architecture, because this is where deep learning is different than conventional software engineering, you can do so much experimentation with all of these things, and you will have different results. And only based on those results, you can say that your model is better than the previous ones or not. So here, let's, for example, keep it like this, and let's create another stack of layers here. So conv 2D, and I'm gonna, for example, use 128 filters, keep them 3 by 3, and the activation is the same as before, so real U. And this approach here, where I take 32, 64, and 128, is also something that I've seen being done in research. So many neural network architectures follow this kind of approach, where each time they double the number of filters. So I'm choosing to do that, but in fact, nothing is stopping you from using other numbers. Here you can use, for example, 100, 110, or just 100, or whatever you like. So I'm gonna finish the architecture using the same approach here. So now I have these layers that are very similar. So we take an input, we do some convolution here, then a second convolution, we max pool, we do batch normalization, then again we do convolution, max pooling, batch normalization. And here, just if I didn't mention batch normalization before, so batch normalization is basically looks at your batches and does normalization on that batch. This is an operation that is inspired from the normalization of the input, which is something that we're going to do a little later. So basically, researchers have noticed that when you normalize your input, this helps the gradient, the computation of the gradient, and it helps when we're trying to minimize our cost function. So some other researchers said, okay, if we're normalizing our input, why not normalize the outputs of the layers inside the neural network? So this is why they created this new type of layer, where it takes the output of this previous layer and then it normalizes the batches. So each time we have a new batch, we normalize the data inside that batch. And finally, since we finished the convolutional parts here, which are the main layers that's gonna affect our neural network, because they can learn so much, and you can check some of the papers about this, maybe the Jan LeCun paper, which was the first one that introduced the convolution or 2D convolution, and you can see how much we're saving in memory and how much they actually improved the results. Now let's get to the part where we basically build what comes later at our neural network architecture. So here I'm going to use a global average pooling, and then I'm going to add a dense layer. I'm going to add a dense layer of 64 units and an activation of real U. So I'm going to keep the same activation function as before. And then I'm going to add a final layer here. And now I'm going to use an activation called softmax. And with this, I have actually finished building my neural network using the sequential approach. And let me just go through these layers quickly and what we're doing here. So the global average pool 2D, it takes the output from this batch normalization layer and it computes the average of those values according to some axes. And then we're going to get a set of values here. And then those values are going to be fed to a dense layer. This dense layer, you can think of it as a vector containing values. So there are no filters like the convolution, like 2D convolution here. And finally, we're going to add another dense layer, which has 10 values. And this will be the output layer of our neural network. And we're choosing 10 here because In our dataset, the MNIST dataset, there are 10 different classes that we can have from 0 to 9. So there are 10 classes. So again, if we go back to the first time I spoke about our classification system, I mentioned that we want to build a system that takes the image as an input, and we want it to tell us at the output which of the 10 categories, so is it 0, 1, or until 9. So this model here reflects exactly that. We're taking an input image, and the output is a set of 10 values, which will be in fact 10 probabilities. We're getting probabilities because we're using this activation function called softmax. So the softmax gives us 10 probabilities, and they sum up to 1. So what we're going to do is look at those probabilities and look at the highest one, and that would correspond to the class predicted by our model. So this basically explains why we're using 10 here and we're using the softmax activation function here. And at this stage here, you don't have as many options as you would have in these layers. For example, in this dense layer, you can choose a different value here. So 128, 100, 32, it doesn't matter. You can change the activation to something else. But at this level here, we are at the output of our layer, and we know that we want to predict one of 10 values. So it has to be 10 here. And also we want those values to be probabilities so that they reflect what the model thinks about our image. That's why we're using softmax here. Apart from this, there's also the input layer where you don't have much choice. You have to set the shape that corresponds to the shape of your dataset. So we know that our images have 28 by 28 pixels, so it has to be 28 by 28 input. We also know that our images are grayscale, so they have only one channel. That's why we have to choose one here. So apart from the input and the output layers, these layers here, you can change so many parameters in them, and each time you train your model and see whether it gives better results or not. So with this, we're actually done building our first neural network using the sequential approach. Now what we're going to do is continue creating the rest of our program so that we can make use of this model, train it, and then test it on some of the examples in our dataset. So now that our model architecture is ready, let's look at how we basically set up the rest of the things so that we can run the training. So the first thing I want to do here is just basically omit this part here. And one thing that I like to do is just use some kind of switchers here so it falls, so that I don't like to comment the code that's important, and also I don't like to delete it, so I just like to use this kind of approach here. And now what we're going to do is the first thing we need to consider is that our data is in some sort of a raw manner. This is how we got it from the load data method here. But before we start to pass it through our model so that it can start to learn, we need to normalize it. So in order to normalize the data, we're going to use some basically division approach. So here we're going to do xtrain, and usually what you would do is just divide it by 255, because our values are between 0 and 255. 255 represents white and 0 represents black. And the thing is, our data set here is an unsigned integer 8-bit data type. Before we do that, before we do the division, we need to basically transform it into another type. So as type, and here I'm going to do float 32 bits. And why are we doing this? It's because if we don't transform it into this float 32 bits type, what's going to happen is that the values that are between 0 and 255, so let's say 200, for example, when you divide it, it's going to become 0 instead of 0 point something. That's because the data is in an unsigned integer 8 bits format. But when we turn it into 32 float format, what's going to happen is that we're going to get that 0 point something, which will not be absolute 0, which is exactly what we want to have here. And we're going to do the same thing for the test set. So test as type, and going to do float 32, and then divide it by 255. So again, why do we do this normalization approach here? It's been by experimentation, we've seen that when you normalize your data, the gradient moves faster towards the global minimum of your cost function. But I have to say that I have done so many experimentations where I didn't normalize the data and it still worked okay. There wasn't that much difference between when I normalized and when I didn't normalize the data. But here, just for the sake of good practices, I'm gonna keep the normalization here. And one thing also that we need to do is to basically make our data set in such a way that our model can accept it in its input. So as you can see, the input model expects 28 by 28 by 1. And here, as you can see, our data set, of course, there are these 60,000 images. This does not matter for our model. It's going to take them batch by batch. But here we see that our arrays are formatted in such a way where we only have 2 dimensions, so 28 by 28, but we want to have 28 by 28 by 1. So in order to remedy this, we're going to do xtrain equals mp.expand dims. So this is to expand the dimensions of an array, and we're going to give it the same array, so xtrain, and then we can use the axis number. So here we want to expand the last dimension. So we know that our array has here 3 dimensions. So of course, when they are 3, that means this is dimension 0, this is 1, this is 2. So we can use, for example, 3 here, and that would work. But you can also do just -1, which means we want to add dimension at the end. So here we're going to do xtest the same way. So let me just copy this. And here I'm going to do test. So now, in fact, our data, let me just maybe copy this and paste it again, just so that you can see the difference. So now our data is normalized because we use this these operations here, but also the dimensions have been changed. So let me just clear this, then run MNIST example just quickly to see what we have differently. So as you can see, we had this shape for our dataset before, and now we have this. And this is the right shape to use with our architecture, because again, our architecture accepts 28 by 28 by 1. Of course, the first dimension that represents the batches, it doesn't matter, so we don't mention it here. So it's not gonna pose any problems. But if we don't have our dataset in this format, it's gonna actually pose a problem. And maybe you will have this question of, why don't we just remove this here? Why don't we just do this, and then we don't need to expand the dimensions? In fact, if you do this, what's going to happen is that you're going to have a problem with this layer here, because the 2D convolution expects a 4-dimensional tensor. What this means is that here we have this tensor that represents the shape of the data, but there will also be a dimension here. It's hidden here, it's not shown, which represents the batches. So we can take several images at the same time. So with adding that dimension for the batches, we're going to have 4 dimensions here. And then the convolution 2D will not complain about dimensions. So that's why we're doing this here, and that's why we're expanding the dimensions here. And okay, let me just maybe remove this for now. We don't need it. And now that we have all of these, all of our data ready to be passed through our model, let's compile our model here. And by compiling, I mean we're gonna set some of the important aspects of the training. So we're gonna do model.compile, and then inside this function here, you have several parameters that you need to set. So there's the optimizer, and there is also the loss, and finally there are the metrics. So these are the 3 important parameters that you need to set. So here the optimizer, what it represents is the algorithm that we're going to use in order to optimize our cost function. And by optimizing, I mean trying to find the global minimum of our cost function. So for this, we have several options in TensorFlow. The most famous one is Adam, which we will be using, but there are several optimizers in TensorFlow. So let me just maybe try to, okay, sometimes it's not giving me option to see all of the parameters, but here we can set the parameter Adam. There's also Ada, and there are several others that you can use. So here, if you go to the TensorFlow documentation and the tf.keras.optimizers, you see that you have all of these options that you can choose from. There's the Ada Delta, Ada Grad, Adam, so on and so forth. You have the stochastic gradient descent here. So you have all of these options that you can use. Again, which one to use really depends on the case that you are doing, and this also goes into the hyperparameters part, where you, for example, you might choose Adam, train your model, and then you might change that and choose, for example, NADAM, and you might get better results using this other optimizer. So it's really an experimental approach, and I do encourage you to change things and see what you can get with those different parameters. So let me go back to our example here. So here, when you want to pass a parameter to this argument here, optimizer, you can just put it between parentheses or between these quotation marks here, and you just write the name, and you can, of course, choose any of the other ones and write it here. And this is how you set the optimizer. The second thing, which is very important, that we need to set is the loss function. So for the loss, for every task in deep learning, you have a set of loss functions that you can use for that specific task. So in classification, one of the widely used loss functions is called cross entropy. So these are two different words, cross entropy, and this is actually a function that uses probabilities, and it computes some sort of probabilities that helps penalize your neural network weights when it predicts the wrong thing, and also helps it know which values are predicted correctly. So there is a lot of research about cross entropy that you can look up online, but in fact, just in TensorFlow, you have 3 different loss functions that have the name cross entropy in them. So here again, I'm looking at the documentation on in TensorFlow, and if I didn't mention it before, I would very much recommend looking at this documentation from time to time. It's written in a quite understandable manner, and you can get a lot of information from it. So again, for cross entropy, if you go to the documentation, you'll see that you have binary cross entropy, you have categorical cross entropy, and also you have sparse categorical cross entropy. So all of them, they have cross entropy in them. So they use this cross entropy approach, but each one of these three loss functions uses it differently. And for us, here we're gonna use categorical cross entropy, and we're gonna use sparse categorical cross entropy, and I'll show you what's the difference between them. So here, let me start by using categorical cross entropy, and I'll explain a little bit later why would you want to use categorical and why would you want to use sparse categorical. For now, let me just finish this part here for compiling our model. So for the metrics, which is the last argument here, we need to set a metric for which the basically we're gonna guide our training so that our model knows that it's becoming better or worse. So here, usually for classification, we would use the accuracy. So the accuracy represents how many examples are we predicting correctly from all of the examples that exist in the data sets. So let's say you have a data set of 100 examples, or let's say images. And when you do the prediction, you get, let's say, 88 images correct, and the rest are incorrect. In this case, the accuracy would be 88 over 100, which is 88%. This means the accuracy is 88%. So this means that your model makes a good prediction 88% of the time. So if now we have 1,000 images, then around 880 images will be correctly predicted. So for classification, this is what we would need as a metric. And of course, here I am using the usual values that are used in classification, but there's a lot of advanced things that you can do. For example, you can create your own loss function, your own optimizer, your own metrics, and then you can pass it here as a parameter. But this is a little bit advanced. So for now, I'm just gonna go through the steps with the usual values that are used in the deep learning community. So now that we have compiled our model, the only thing that's left is to fit the data into our model. So for that, I'm gonna call model fit, and the fit function takes several parameters. The first parameter is the xtrain, so the images, and then it's gonna take the ytrain, so the labels corresponding to those images. It's also gonna take a batch size. So this batch size represents how many images is our model going to see each time. So here you can, for example, if you set it to 1, this means that we're gonna pass 1 image at a time through our model. But we usually don't do this. We usually choose a larger number of images to pass them through our model. So here, for example, we can use 64. This is also one of the hyperparameters that you can change and see how your model will perform based on different values. And also, we're gonna set the parameter epochs here. And let's say I'm gonna choose, for example, only 3 epochs so that we can quickly do some experimentation. And the epoch represents, one epoch in fact represents the fact that your model has seen all of your data set once. So when all of your images are passed through the model, if this is done once, then this is one epoch. If your model has seen them twice, then these are two epochs, so on and so forth. So basically here we're defining the number of times that your model is going to look at all of your data set. This is also a hyperparameter. So here, in fact, we can keep it just like this and we can run the training, which means that all of the images that exist in the train set are going to be used for training. But one thing that you can do, in fact, is use a validation split. So a validation split here, for example, let's say I'm going to use 0.2. This means that I want to use 20% of the train images for validation. So again, what does validation mean? What is it? Why is it different than the test set, for example? In fact, when doing cross-validation, usually you split your data into the train, the validation, and the test sets. You split them into these three parts. The train set will be used to train the model. The validation will be used at the end of every epoch. We're going to run the model on the validation, not for training, but just for prediction, so that we can see how well the model is doing on data that it did not see, it did not use to train. So these two splits are the ones we use to fine-tune our model. So when I mentioned hyperparameters, I mentioned that this is, for example, a hyperparameter. This is a hyperparameter. The values here are hyperparameters. But when do you say that one or a set of hyperparameters is better than another set of hyperparameters? In fact, you do this using the validation split. So whenever you train, you test on the validation split or on the validation part, and then you see whether that metric that you're using has improved or not. So in our case, the metric is the accuracy. Is the accuracy becoming better when we change the hyperparameters? So you do one training with a set of training parameters. You see the validation set, is it good or not? And then you change the hyperparameters, you run the training again, and you look at the validation accuracy. Did it become better? Did it become worse? And you keep doing this loop of experimentation until you get to a point where you see that you're not improving anymore on the validation set. And then only when you're done with this experimentation phase that you keep the final model that worked well on the validation set, and then you test it on the test set. So with this parameter here, validation split, what we're going to do is split our training set into two parts. 80% of the training images or the images that exist in this xtrain variable are going to be used for training, and 20% of them are going to be used for validation. And then we're going to keep the tests set here until the end when we finish the training, and we're going to use it to evaluate our model to see how well it performed on images that it has never seen. So the images here, whether they are in the train set or the validation set, the model is going to see them at some point during the training. But the test set, we're not going to use it in this function here, which means that the model will never see it during the training, and we can pass that set of images to the model only at the end of the training. So for example, we can pass it here, model.evaluate, and we can give it the xtest, ytest, and we can also choose a batch size here. Let's just keep it the same as before. So again, just to summarize quickly what we're doing here, we're taking the train images, so 60,000 images. We're going to split them into two parts. 80% of the images So 80% of the 60,000 images is going to be used for training. The rest, which is 20%, is going to be used for validation. And the test set, which is the 10,000 images here, are going to be used at the end when the model has finished training. So at this point here, this is model training. Once this line here is done, then the model is trained, and here we can do evaluation on test set. This set here, the X test, is going to help us identify how well our model is going to perform on data that it has never seen. Because usually what you do is you train a model, you put it in production, and then you start testing it on new data that's coming from, for example, your users, if you have some sort of a web product. And those examples, the model has never seen them. So in order to get an idea of how well your model will perform on examples like that, you keep this part here separate from the training and the validation. You keep it until the end, and then at the end you test your model on it. So this is the goal of this test set, and the goal of splitting this set here into two parts. Now we have a complete program that we can run, and we can train our model, and we can see how well it performs on train, validation, and test sets. So let us do that right now. Let me just clear this, and I'm gonna run our example here. So this might take some time, depending on your machine, but usually it shouldn't take that long. Well, in fact, when I ran the code, I got into this error here. And in fact, I wanted you to see this error because it's a very common error. And I wanted to use it in order to explain to you why you would want to use categorical cross-entropy or sparse cross-entropy. In fact, this error is coming from this specific detail here. So when you have a data set like we have here, if you use categorical cross-entropy, then in fact this loss function is gonna expect your labels, which are these ones, the Y train and the Y test, is gonna expect them to be one-hot encoded. And if you don't want to use one-hot encoding, then you need to use a different loss function, which is the sparse categorical cross-entropy. So this is a minor detail, but it's very important. So if you go, in fact, to the documentation, so here in the documentation, I just opened the 2 pages for categorical cross-entropy and for sparse categorical cross-entropy. So for the categorical cross-entropy, here, although it's not specifically mentioned here, but in fact, if you look at the example, you see that this is how you would use categorical cross-entropy. This is how your labels need to be set. So in fact, this is one label for one image, which is in a form of a vector. And in that vector, the 1 will correspond to the right class, and the zeros will correspond to the wrong classes. So if you have 3 classes, then you need to set 1 to the right class and zeros for the rest. In our case, if we wanted to do one-hot encoding, then, for example, if you have, let me just do this quick example here. If you have label 2, then one-hot encoding will be like this. It will be a vector of 0, 0, 1, then 0, 0, 0, and 8, 9, 10. This will be the corresponding label for that image. So the image contains the number 2, but your label needs to be like this. And this is called one-hot encoding of your labels. Now, if in the case how we're using our data set, in fact, we're not using one-hot encoding. So our labels are just encoded as numbers. So if it's number 2, then the corresponding label is 2. If it's 0, then it's 0, so on and so forth. We're not using one-hot encoding. So if you use categorical cross-entropy, then you have to use one-hot encoding, which means that you have to take the Y-train, Y-test, and turn them into one-hot encoded labels. And if you don't want to do that, you need to add the sparse categorical entropy here instead of the categorical cross-entropy. Because if you go to the documentation, you look at the sparse categorical cross-entropy, you see here that we're using labels in the format of the normal format, not the one using one-hot encoding. So when doing this, if we save this, let me clear this again. If I run my example, now we should have no problems. Everything should be running smoothly. And as you can see, the training has started here. And let me just stop it here just to show you if you were to use categorical cross-entropy, what would you need to do differently? Because sometimes you might have a data set that already has one-hot encoding labels. In that case, if you just want to use them as they are, you don't want to transform your labels into a different format. In that case, you would just use categorical cross-entropy. But if you have labels like this that are not one-hot encoded and you want to turn them into one-hot encoded, what you can do is use a utility from TensorFlow. So here we're going to do ytrain TensorFlow.keras.utils.toCategorical, and then you would give it the same array, so ytrain, and then you want to tell it how many classes you have. So we have 10 classes between 0 and 9, and you would do the same for the ytest. TensorFlow keras utils to categorical, and here I want to give it test and 10 classes. So now if I do this, then in fact I'm transforming my labels into one-hot encoded labels, and in that case I can use categorical cross-entropy. So let's run the training again and see if this works or not. So as you can see, the training has started correctly with no problems. And I hope now you understand the differences between categorical cross-entropy and sparse categorical cross-entropy, and when to use which. So I'm going to wait for the training to finish. I've only set the epochs to 3 because it already gives us some good metrics here. And it's done. So let's go a little bit over the logs here, and I would like to explain to you what these things mean. So this one here, the first number here, 11 seconds, represent how much time we spent doing this one epoch. And also this tells us the speed, so 12 milliseconds per step, and the step here means doing a full batch. So we have a batch of 64 images. So the model is processing 64 images at the same time in 12 milliseconds. And by doing that, the first epoch, we got a training loss. So this loss here is the training loss of 0.2368. We have an accuracy of around 93%. We have a validation loss of 0.0994, and we have a validation accuracy of around 97%. And what this means is that, as you remember, we did this split here, validation split. So the first loss and accuracy are reported based on the 80% of the data that we used for training, And this part here for the validation is reported based on the 20% that we left out for the validation. So it's 20% of that extrain. And after each epoch, we get these values so that we can see the development of the loss and the accuracy. And what you want to get here is a lower loss during the training and a higher accuracy. And at the end, this last line here, we've actually ran it over the test set just to see how well our model, our final model that we got here, how well is it doing on the test set. And here we see that we got a 98.36% accuracy, which is not bad on this task. So as you can see, now we have a full program that has a deep learning model, and it compiles that model with specific optimizer, loss, metrics, and then it fits the data into that model. And when we're doing evaluation, we're getting some good results. So with this, we have finished the first, let's say, part of doing training for an image classification task. And as you can see, with TensorFlow, it makes so many things easier. You don't have to do a lot of things. You just need to set the right parameters and prepare your dataset in the right way. So now that we have this first version of our program working, let's see what we can do next. This first model that we created and we trained was using the sequential approach here, where we just stacked different layers. And now let's take a look at the other approach that we can use, which is the functional approach. So first, let me just maybe change this to sequential model, just changing the name here. And here, what we want is to build the same exact architecture, but in the functional approach. So in fact, to do this, you just need to create a function, and let's call it, for example, functional model. And here you need to use these same layers that we used in our sequential model, but we're going to use them in a functional way. So let us just maybe copy them from here and just paste them here. Let me fix the indentation. And in order to build a model using the functional approach, what you need to do is basically define a set of layers, and each time you need to pass the output of the previous layer as an input to the new layer. So here, for example, I would call this my input, and then for the convolution 2D, I need to actually pass my input as a parameter to this convolution 2D. And then I need to store this into a variable. And I need to do this for the rest of the layers. So each time I have an output of a layer, I need to pass it as an input to the upcoming layer. So let me just do this quickly here. So now I have done exactly what I explained to you. I'm just using each time the variable x to store the output of a certain layer. Then I'll pass that variable as an input to the next layer. And I do this for all the layers. Oops, I forgot this one here. And okay, we have it here. Here we have it everywhere. And now when you finish doing this, you need to basically create the model where you tell it that this is the input and this is the output. So the input is this, and each time we're passing it through our layers, and we're getting an output here, which is x. But in order to construct a deep learning model that you can call the compile function and the fit function on it, you have to use the TensorFlow.keras.model class. And here you need to give it inputs, and it's going to be my input, and also outputs, which is going to be X. And then you return your model. So this is how you would build a deep learning model architecture using the functional approach. So as you can see, it's the same exact model. It's just that we're building it differently. Now, why would you use this approach rather than this sequential approach? Well, in fact, the sequential approach is rarely used when you're building deep learning models for some, let's say, complex tasks. And even for smaller tasks, I think it's better to build your model in this way here, because it's much more flexible. You can do so many things. For example, if you have, let's say, two different inputs, you can just set them here. This will be a list of inputs where you just add the inputs to it. The same thing if you have several outputs. So it's a lot more flexible, I think, and also it's going to allow you to, for example, you can build one part of the model, then create another part, then use those two parts into when building a larger deep learning model. So this is a much better approach in my opinion. I've only seen the sequential approach here used in some tutorials online because it's easy and it's basically allows you to quickly build something that you can manipulate. But for real world projects, I think that using this functional approach is much more recommended. So now that we have this, we can just go to our code here. Sorry, let me just close this here. Here, I'm just going to call my function. So model, functional model, and then I'm just going to call the same exact methods on it. So the compile method, the fit method, the evaluate method. And what's also good about this functional approach is that you can make this architecture much more flexible. For example, by adding parameters to your function that you later add them here. For example, the number of filters here, the filter size here. You just add them all as parameters here, and then you can generate several models quickly. You can just create, for example, a for loop, and you create several models with different hyperparameters, and then you compile them and fit them and compare between them. So as you can see, this would be a good use case for functional model instead of using sequential model. So now that we have this, let's run our code again and see if this works or not. So let me just run this. So the training should start, and it did. So as you can see, we have just defined the same architecture in a different approach, which is the functional approach, and it's working well. The loss is going down, the accuracy is going up, and let's just wait for it to finish. This should not take long. It's going to run the evaluation on the test set here. And as you can see, we got the results here from our functional model, and there was no problem during the training or the evaluation. So this is the second approach that you can use to build deep learning models. The third and last approach is by using or by inheriting from the TensorFlow.keras.model class, and which is what we're going to do next. To build a deep learning model architecture using this third approach, you start by creating a class. You can give it any name you like. So for me, I'm just going to call it my custom model. And then you need to inherit from the class TensorFlow.keras.model. And in Python, to do that, you just add parentheses and you add the class that you want to inherit from. So here, model, Let's start with the instructor here. And here we're calling it on the mother class, which is this class here. Let me just maybe remove this. We don't need to use it. And now what you would do in this third approach is that you need first to define all of the layers, and you need to give them a name. And then you would use you would call the function, in fact, implement the function call, which is just like this. And then you can give it your input. And then here, what you would do is you would pass your input throughout your layers here. So you start with the first layer and then you continue. So to make this more clear, let me just do this here. First, we're gonna define all the layers. And again, I'm gonna use the exact same architecture, and just we're implementing it in 3 different ways so that you can compare between the 3 approaches. So here, I'm just gonna start by creating these layers and giving them names. So here I have just done exactly that. As you can see, I call my first convolutional layer self.conv1, self.conv2, so on and so forth. And here, when I go to my call function, here I can start calling them. So my input needs to be passed through this first layer, and then the output of it needs to be passed through the second layer, so on and so forth. So this is what the call method here needs to do. So let me just do this quickly now. So I have just finished doing exactly that. I take my input, I pass it to my conv1 self.conv1 layer, which is this convolutional 2D, and then I get an output, then I pass it to the second one, so on and so forth. And at the end, I need to return X. And this might look a little strange, this approach, compared to the other ones, but this is also one of the approaches you can use to build custom models, especially if they're much more complex than this. You can do so many things when you have a class specific for your TensorFlow model. And in fact, if you've worked with PyTorch before, then this should be very familiar to you, because it's very similar to what PyTorch does. In PyTorch, you do the same thing. You define the layers first, and then there is a method. I think it's forward, if I'm not mistaken, instead of call. And then you do the same thing. You pass the input to the first layer, and then the output to the next layer, so on and so forth. So with doing this, we just finished defining our model using this third approach, and we can use it to in practically the same manner we used the functional and the sequential model. So let's see how we can do this. So I'm just gonna comment this one here, and now instead of using my functional model, I'm just gonna use my custom model. So just calling or instantiating an object from my custom model class, I get my model, and then I can do exactly the same thing. I can compile my model, I can fit my model, I can evaluate my model. And let's test this quickly here. Let me run the example again. So, okay, it is right. Okay, now the training is running, and as you can see, we're doing the exact same thing as we did with the first 2 approaches. And now you have seen the 3 different approaches used when creating an architecture for a deep learning model in TensorFlow. And you can use whatever you like. You can also use them all 3 depending on the task that you're doing and depending on the specific circumstances. But here, as you can see, we defined the same architecture in 3 different approaches, and we were able to fit the data and evaluate our model, and the results are very close. So now you have all of these tools and these approaches that you've learned, and we use them on the MNIST dataset. Let's see now what we can do next. So there are some things that I omitted in this first tutorial here. I wanted to only show you the main parts that you need when training a deep learning model. But in fact, you can do a lot more things, and there are some necessary parts that I didn't mention here. So for example, one thing is about saving the model. So here we're just doing the training and evaluating the model, but we're not saving anything. So what if I want to use this trained model in production? What if I want to use it in some sort of a web app or an embedded application? In that case, I would need a model that I can take and then I can run in a separate script that just loads the model and makes predictions with it. Something else that I didn't do is saving the best model during the training. So there's one thing you can do here. We just save the final model. But if you notice here, for example, let's see if we have a good example. Yes, okay, so you see this second step here, we have a higher accuracy than the last epoch. So it's actually better to save this model that was finalized in this epoch rather than the last model which was saved, or it wasn't saved, but which we got at the third epoch. So we're not doing this now. We're not saving the best model. We're not saving any model, in fact. I wanted to show you this in this tutorial, but then I thought it would be better if we leave this in the next tutorial that I'll show you, which will represent a real world scenario, because here with the MNIST examples, which are the Hello World equivalent in programming, you have the MNIST dataset already prepared for you. You see, we just used it. It's part of the TensorFlow framework. So we're just loading it, and then we are using these images and labels when training our model. But if you're working on a real world case, then maybe you would have collected images by yourself. Maybe you went outside and captured some images here and there. So in that case, you need to create your own data set that is compatible with TensorFlow and that you can use it to train a deep learning model that you would define just like we did here. So I wanted to leave these details of saving the model during the training and saving the final model, the format of saving the model. I wanted to leave them for the next tutorial that we're gonna do. So with this first tutorial, you should have all the necessary steps that you would use to train a deep learning model for classification. Many of these, or most of them, in fact, most of these parameters, most of these things that we've done here, we're gonna redo them in the next tutorial, but just we're gonna go into maybe more details about specific things like the data set, how to create a data set that you can use just like the Keras or just like the MNIST data set, sorry, how to save the model during the training, how to save the final model in the saved model format, and things like that. So for now, this is it for this tutorial, and let's take a look next at what we can do in a real case scenario. So before we continue along the course, let's maybe restructure a little bit our code for better readability. This is something that you're gonna find yourself doing often when you're developing projects for a company that you're working for. And by doing this, you're actually gonna make your life easier in the future because you're gonna have all of these different modules that contain different parts of the code, and many of them will be reusable modules so that you can use them in other projects as well. So the first thing we're going to do is maybe move these two models, the functional model and the model that inherited from this class, into a different file. So for that, let me just create a new file and maybe just call it deep learning models.py. And what I'm going to do here is just move these parts of the code. So let me just move these, Control X and Control V. And here I can just import the same modules or the same functions and classes that we used in our code. And also I'm gonna import, of course, TensorFlow because we're using it here. And by this, we're gonna have our models in a separate file, and then we can just come to our main script and do, for example, from deep learning models, import functional model and also my custom model. So as you can see, we moved a large part of the code into another file, and now we have this file here that just contains the deep learning models. So maybe we can use these models in different projects, and we will find them in a separate file instead of finding them in this script that's specifically made for MNIST dataset. Another thing we can do, for example, is move this function here, display some examples, to a different file. So maybe we can call it, for example, my utils.py. And also, okay, let me close this. I'm gonna come here and just cut this and paste it here. And here, of course, I'm gonna have to import matplotlib.pyplot as plt, and also I need to import numpy as np. So now we have this, and of course we can import our functions the same way from myutils import display some examples. And now, as you can see, a large part has been moved from this file. And now this file is specifically made for the MNIST dataset, and we're importing the necessary models and functions from our other files that we just created. So I am showing you this here just as an example that you can use for your projects, because when you're working for a company and you're building AI projects, machine learning models, you're going to find yourself doing lots of experimentation. You're going to find yourself reusing parts of your code. So if you get used to this habit of taking different parts of the code that are reusable and putting them into separate files, this is going to help you a lot, and your future self is going to thank you. And with this, that would be it for the coding of this first tutorial. Let's see what we can do next. So let's just recap what we have seen in this first tutorial. So basically, we took a look at the MNIST dataset. We saw how we can load it from the TensorFlow datasets. We explored that dataset by implementing a function that can go through the dataset and randomly choose some images with their corresponding labels. We took a look at the TensorFlow layers, how to import them, and then we saw how we can use those layers to build a neural network architecture in 3 different approaches: the sequential way, the functional way, and by inheriting from the model class. At the end, we compiled our model and fit the data. And we finished the tutorial by restructuring our code for better readability. So with this would be the end of this first tutorial. Let's see what we can cover next. Welcome to this second part or second tutorial in this introductory TensorFlow course. So in this tutorial, what we want to achieve is something like the following. So we're going to have a data set of traffic signs like the ones you see here. And the goal would be to develop a deep learning model that can take an image of a traffic sign like this one, and then it gives us at the output that this image actually corresponds to the traffic sign of speed limit 100 kilometers per hour. And maybe it will not tell us exactly this expression here, but maybe it can tell us that it's 1 and that 1 corresponds to this speed limit 100 kilometers per hour. And if we change the traffic sign, we want to get the corresponding sign here. So we're going to be developing and building and training this deep learning model, and this will be the goal of this second tutorial. The dataset that we will be using for this tutorial is called German Traffic Sign Recognition Benchmark. So this dataset, you can find it on Kaggle. So if you don't know the website Kaggle, it's a website that many data scientists, machine learning engineers, and just anyone who's interested in machine learning uses it because it has so many data sets. It also has some competitions that you can join, and you can even be part of a team, and you can learn a lot by doing that. So this dataset, in order for you to get it, you can go to this link here, and if it's maybe the link is not that clear since we see so many meow here, you can just take the German traffic sign recognition benchmark expression here, and you can look it up. Let me just maybe go back to make it clear. So if you're on the Kaggle website, you're gonna go here on the search bar, type this and look it up, and it should be the first result. And then you're gonna get to the same page that I showed you earlier. Just a quick note here. So in order for you to get access to the dataset and download it, you need to have an account on Kaggle. It's completely free. I already have one and I'm already logged in. But if you don't have an account, you can just create an account for free, and then you can continue with going to the dataset page and download it. So in order to download the dataset, you just click on the button download, and then it's gonna download it to your own machine. And once it's downloaded, it's gonna be a zipped folder like this, and then you can unzip it in order to get a set of files and folders like this. Just a quick note here also, when I was unzipping this folder here, I realized that I think the dataset is duplicated. So many files, it asked me that whether I want to replace them or just keep both versions. When I was unzipping this file here, I chose to replace them so that I don't have a duplicate of every file and every folder in my dataset. I think this is maybe a mistake that was done by the person who collected or put the dataset on Kaggle, but it's not a big deal. You can just unzip the folder, and when it asks you whether there are new files and folders that have the same name, just choose replace or choose do not replace for the rest of the dataset, and that way you won't have any duplicated folders and files. And now that we have it here, and as you can see, I unzipped it, we see that we have 3 files and 3 folders. So the main files and maybe the main folders that we're gonna be looking at are the test and train folders, and also the test.csv file. So let's first go to the train folder here. So as you can see, we have 43 folders, so from 0 to 42, so 43 folders, and in each folder we have images that belong to the same class. Let me see if this is the large. Let's see, it's the same. Okay, so for example, we can see here that this is a sign for the traffic sign that says there's a speed limit of 20 kilometers per hour. We also have this data set here of the speed limit 50. And we have all sorts of speed signs, as you can see. And what I really like about this data set is that the images represent real life cases, not like the MNIST example where the data set is more or less already prepared for us. But in the case of these traffic signs, we see that these signs are taken in different luminosity levels, different light levels. It also comes in different sizes, so different images have different sizes. They're not all the same. And also, if we go to the next folder, which is the test folder, here you can see that we have a set of images, and we can't know just from the name, for example, whether this image belongs to class 1, 2, or whatever. So we can't know from just looking at the image and looking at the name of the image. In order for us to know each image belongs to which class, we need to go and look at the CSV file corresponding to that folder. So test.csv for the test folder. And let me just open it here. Okay, let me close this. So here, as you can see in the test.csv file, we have different lines corresponding to different images. Each line has these width and height of the image, also has a row area. I guess it's a more tightened area around the traffic sign. We also have the name of the image, and we have the ID of the image. And these are the two most important information that we need from this. So we need the path, and for each image, we need to know the corresponding class ID. So here, let me just maybe open this close. So let's go to the test. So for example, the first image, 00000.png, it says that this belongs to class number 16. This is the class ID, so it's 16. And if we want to just quickly verify, just remember this is, I think, a traffic sign that says that trucks cannot pass through here, or only for trucks. I can't remember, honestly. And if I go to the train set and I go to class 16, as you can see, it corresponds to the right class. So from what we see here, we have two folders. The first one for training, the second one for the test set. The test set is not organized like the train set. In order for us to know which image belongs to which label, we have to look at the CSV file. And there's also the fact that we only have two sets. So there's only the train and test set. But in reality, what you want to have when you're developing deep learning models for real life cases, you want to have three sets. You want to have a train set, a validation set, and a test set. So there's a lot of work to be done before we can train a deep learning model on this data set. And this tutorial for me represents a much more mature case of a machine learning project where basically you are using a real life data set. If someone collects it, maybe he chooses to annotate the dataset like this, where it just puts the images in one folder and keeps a CSV file corresponding to those images and their labels. So as you can see, it's not very clean, not like the case where we had the MNIST dataset, we just basically loaded it. So now in order to build a deep learning model on this dataset, we have to basically do some cleaning and also some preparation of this data set, and this is exactly what we're gonna be doing next. So the first thing we're gonna do now to prepare our data set for training is to go to this train folder, and we're gonna split this data set here that exists in this folder into two different folders, one for training and one for validation. So basically what we want to do is to create some function that can go through all of these folders, and each time it goes through the images in every folder and it takes part of them and puts them in a training folder, and the rest it puts them in a validation folder. So let's start by coding this. And before that, let me just maybe add a new script. We're gonna call it street signs example.py. So this will be for all the necessary code to basically load the data set and also train the model and evaluate it. And here, maybe let's first start by defining a function that's gonna split the data. So let's call it split data. And what this function is going to take is the path to the data, so the original folder, which is this one here. We're gonna take a look, or we're gonna look into this folder here, and then we want to split the data into a training folder, so path to, maybe let's call it save train, and also path to save val for validation. And we're also gonna choose a split size, and it's going to be between 0 and 1, and I'm just gonna give it a default value of 0.1. And what I want is for 90% of the data to be put in the training folder, and the rest, which is 10%, is going to be put inside the save for the validation folder. So here, let me come here, and the first thing we're going to do is basically get the folders. So I'm going to use os.listdir, and I'm going to give it the path to data. And since we don't have this module, let me import it here. So what this line here is going to do is basically it's going to give us a list of all the folders that exist inside this directory here. And then what I want to do is to iterate through the folders. So I'm going to do for folder and folders. And here, first, I want to get the path to, or maybe let me call it full path, which is going to be the path or the full path to the directory. So here, we're going to have this path, and then this first command here is going to give us the folders. Now we want to concatenate the name of the folder with this path here in order to get the full path to this set of images, for example, or this set of images. So here I'm going to use os.path.join, and I'm just going to use the path to data, and also I'm going to concatenate that with the folder. After that, what I want to get is a list of all the paths to the images inside that folder. So I'm going to call it images paths. And for this, I'm going to use the module glob. So it doesn't exist here. So let me just import glob here. So this module is going to allow me to look inside a folder and load all of the files that exist in that folder depending on an extension that I choose. So here what I want to do is use os.path.join, and I want to join the full path that I just constructed, and also I only want to load the images. So our images, let me just take a look quickly. All of our images have a PNG extension, so I only want to load PNG files. So here, by doing this, what I'm saying is that I'm telling this glob module to give me a list of all the files that have extension PNG inside my inside this folder here, full path. So now we have a list of all the images inside that folder, and what we can do now is we can, for example, do xtrain and xval, and we want to basically split the data set into these two different parts. And for that, there's actually a utility function called train test split, which we can import from the scikit-learn module. So here, if I do from scikit-learn that model selection, import train test split. So by doing this, I'll be able to use this train test split function here. And what this function takes is basically the images paths, and also it's gonna take the test size. So this is going to be the fraction that represents the number of images that we want to put inside this variable here. And for this, I'm just gonna use my split size, which I pass here as an argument. So what I'm saying here is that please split all of please split the list of all of the images here into two parts, train and val, for validation. And I want this second part to be only this fraction of the dataset, which is if we keep the value as it is, then it's going to be 10%. And if we call the function and we change this split size, then it's going to take that exact fraction. So now we have our train and validation paths. And what we can do now is basically just go through them. So first we're going to go through for x in xtrain. So we're going through all of the images that were selected for the train set. And the first thing we're going to do is get the name of the image. And in order to get that, we're just going to use the function os.path.basename, and we're going to give it x as the argument here. And remember, this x represents a full path. Here we want to get just the name of the image. So we would like, for example, to get this only this 5 zeros, 5 zeros, 5 zeros.png. So this is what we're gonna get as the base name. And then we're gonna use basically this base name to reconstruct a new path that points to this path here, and we're gonna save our image inside this path here. So let us first do this folder. I'm gonna construct a path here, os.path.join, and I'm gonna do path to save train and folder. So here what I'm doing is imagine that, for example, I want to save my images into this. Let's create a new folder, for example, and let's call it training data. And inside of this, I'm going to create a folder called train and another folder called val for validation. So what I'm going to do is take the images from folders like this and just go, for example, to the train set or the train folder and just put that image here. And for now, I'm just going to copy the images. I'm not going to move them, just so that I keep the original dataset as it is. But first here, I need to add a folder, for example, 1, 2, 3, that corresponds to that specific label for that image. And that's why what we're doing here is we're constructing this full path here. So this is going to be this path. And then we're going to add a folder with the same name as the folder that we found in the original data set here. And after that, what we're going to do is check if this folder does not exist. So path to folder, if not os.path.is directory. So this is going to check whether this folder exists or not. If it doesn't exist, we're going to create one. os.makeDirs. So this is to create that folder. And I'm going to do path to folder. So this part here just checks whether that folder exists or not. If it doesn't, it creates that folder. And now what we're going to do is use the utility module shutil, and I don't have it imported, so I'm going to import it here, shutil. And this module here gives me access to several functions. One of them is the copy function that I can use. And now what I can do is basically copy my image and put it inside a new directory that I just constructed here. And if it didn't exist, I would have already created it here. And now I want to put my image inside this folder. So what we can do is actually two things now that I'm looking at it. We can either do path to folder, and this is going to copy the image with the exact name that it has inside this folder, or we can construct a complete directory with the name of that image. So basically, we don't need this here. It's in fact just going to take the name of the image and put it inside the new folder. So this is going to be for the train set, and we're going to do the same thing for the validation set. So I have just added the part here for the validation, and it's going to be identical to the train set. The only thing I'm doing is looking at the original directory, going through the folders, constructing a new folder inside the train and the validation folders, and then copying that image from the original dataset or the original folder into the corresponding folder, whether it's train or validation. And now that we have this, let's test our function. And I have also here activated the virtual environment that we used before, which is tf2venv. And in order to do that, you can just point to the folder where you have Miniconda 3 installed on your machine in order to use the script called activate, and then point to the name of the environment that you have. And also something that may be a quick way to do this. Let me just clear this first. In fact, if you're on Visual Studio Code and if you have already used a specific virtual environment with Miniconda before, then what I have noticed is that if you click on the plus sign here, it's going to open a new terminal and also is going to activate that environment automatically. So you can use this quick way to activate your virtual environment. And now that we have this, let me maybe first activate or save my script here. And one thing you can notice is that this script or this module sklearn is not recognized. And just to reiterate what I showed you in the first tutorial, if you click on Ctrl-Shift-P, you can choose the right interpreter. And here I'm making sure that I am using the same virtual environment, so it's TF2VM, and this module is not installed inside this virtual environment. So for that, you can do a quick pip install sklearn for scikit-learn, and this is going to install that module if it's not already installed. And once this is done, then here we can do the same thing as we did before. So if name equals main, then I would like to do a set of things here. So I'm gonna basically choose the paths that I want in order for me to split my data set. So the first path needs to be towards my original set, which is this one. So I'm gonna do this, Control-C, and here I'm gonna paste it. I'm just gonna add these backwards slashes here, just so that I don't get any problem. And if you are on Linux machine, I believe that this is a safe way so that you don't face any problems, because between Windows and Linux, they handle paths differently. But if you do two backward slashes like I'm doing here, then you shouldn't face any problem. So this is the path to data, and then path to save train. So this is going to be the path where I want to save the train part. So I want to save it here. Control-C, Control-V, and let me fix these as I have done before very quickly. Okay. And then I want to basically paste the same path here. So path to save val, and let me paste it, except that is going to point to the val folder, which is this one here. So now that we have our three different folders or paths, we can call our function called split data. So it's going to take path to data, path to save train. Let me just make sure that I'm using to save train, and also path to save val is path to save val. And for the split size, we can keep it as it is, so we don't have to call it here. And let me just save my script. Let me clear my terminal. So the goal is to copy the images from the original folder into these two folders, and it's going to put 90% of those images in the train folder and 10% in the validation folder. So let me run this script quickly and see if it works without any problems. So here it's this module should be installed, so there should be no problem here. And now the script is actually running. It's just that we don't see it work because we don't print anything. But if you go here, you see that it started to construct these folders in both the train and validation folder. And in each one, we should have a set of images like it's shown here. So this might take a little bit of time because we have a lot of images. At the end, I'll show you what we get, and all the images that were copied, we're going to see that they have been correctly copied with the correct split size that we chose. So now the script has finished and the program has finished working. And if we look at our data here, we see now that in my train folder, I have 43 folders, and the same for the validation folder. And in fact, if we check quickly the number of images, here we see that in the train set, we have around 35,000 images. And in the validation set, we have around 4,000 images. So that sounds about right. So the split size seems to be correct. And if we go to every folder, we have the exact same images that we had in the original set, which was this one here. So now we have our training and validation sets. What we need is the test set. And as you remember, the test set is comprised of images like this. And in order for us to know which label, basically which label corresponds to that image, we need to look at the corresponding CSV file. So for that, let us create a function that does this. So our function is going to take as arguments the path to the folder and the path to the CSV file. And based on these two, we're going to construct a folder that contains the right images, just like this. So we want to order our test set so that it starts looking like this folder here or these folders here. So let us get into this. And maybe since this is also a utility function, maybe we can just remove it from this main script and maybe add it to our utilities script. And here we need the OS module, so import OS. So, and also import glob, and finally the scikit-learn from scikit-learn.model selection import train test split, if I'm not mistaken. Let me check this. Train test splits. This sounds correct. And also we need the shutil. So these are the modules necessary import. So these are the modules necessary to run these functions. And now here we don't have that. We can also remove these if we want. For now, I'm just going to keep them. It's not a problem. And here I'm going to do from my utils import split data. So this is a much cleaner script. And now let's maybe do the same for the test set as I mentioned. So we want to build this function that orders the test set. So let's call it, or maybe let's just code this straight in the utilities script here. So I'm going to define a function called order test set. And what this function is going to take, as I mentioned, the path to the images and also path to CSV file, or just CSV is clear. And here what I want is to construct a dictionary that basically has the name of the image as the key and also the corresponding label as the value. So let's start by defining our dictionary. And by the way, this dictionary here is just going to help us keep track of the dataset later if we want, but it's not really necessary for us when we're just ordering the test set. I just prefer to do this so that I have, or I could have some sort of a data structure that contains my image paths and also their corresponding labels. But for you, it's not really necessary for our ordering part, because as you remember, we just want to go through these images and just order them like we have here. So here, let me start by creating a try block. And what I'm going to do here is to open my CSV file. So path to CSV, and the mode is read. I don't want to write this inside this file. I just want to read, and I want to open it as CSV file. And then I can create a reader, and it's going to use the module CSV.reader. And since we don't have the module CSV, we can import it here. And just maybe a quick note here, if you see me using a module that's not installed inside your virtual environment, then it's very easy to install any module you want. You just run pip install the name of that module. So here I'm gonna use this function or this method here, and I'm gonna give it my CSV file, and also I'm gonna choose the delimiter to be a comma here. And why comma? Because inside my CSV file, you see that these elements are separated using a comma. And now what I want to do is basically go through all the rows that exist in this reader, because this reader is going to contain each row inside my CSV file, including in fact this first row here that only contains information, so only the headers, which we don't need. So we need to make sure that we don't use that information in that first row. So that's why we're going to do for I row in enumerate reader. And the first thing I'm going to do is check if I'm looking at the first row. And if I am, I'm just going to continue, which means that I don't want to use any information in that row. I just want to go to the next one. And for the rest of the rows, what we're going to do is first get the image name. And for that, what we can do is use our row. And in fact, our row is going to contain all of the elements inside that row. So it's going to contain this value, then this, and this, and this. And you can access them using the correct index. So row 0 is going to access this value here. And row -1, for example, is going to access the last element, which is the path to the image. So here, what I want to do is get the image name. So for that, I'm going to get the final or the end value inside that row. And remember that each image here, this is how the dataset was constructed. So we don't just have the name of the image, we also have this test and / next to it. So we don't want it, we just want the name of the image. So for example, the first one would be 00000.png. We just want this, we don't want this part. So what we're gonna do here is, since this is a string, we're gonna use the method replace, and I want to replace this string here with an empty string. This means that we're gonna take this full information, we're gonna remove this, and we're just gonna keep the name of the image. And the second thing we want to get is the label. So for the label, this is going to be row -2, and that's because this is the second element starting from the end. So this is class ID is the second element from the end, or it's 0, 1, 2, 3, 4, 5, 6, sixth element. So we're gonna use this, or you can do just this. For me, I think this is much cleaner, -2, because now I know just from the end, I'm just gonna look at the second value there. And then what we're gonna do is construct a path to folder. And this is going to be a path that that is constructed using the path to the images and also the label. So path join path to images and also label, since it's a string. And then I'm gonna check if this path does not exist. Path is directory path to folder. If it doesn't exist, I'm gonna create it. And here I'm gonna do os.makeDirs path to folder. So this is exactly what we did in the previous part. So I'm just redoing it here. And now what I want is to move my image from the original set. So here, from the test set here, I want to move it into this new folder that corresponds to the right label. And you'll see in a minute what I mean by this. So here, I'm gonna do image full path, os.path.join path to images, image name. So I'm constructing a full path, and then I can do sh-util.move. You can either copy or move the images. I showed you before in the previous function here, we copied it in this one, split data, and now we're just gonna use the utility function move. So for this, we're gonna move the image, so because we just got the full path to that image, and we want to move it into the right folder, which is path to folder. And this would be it. Here, I'm gonna use the except command so that if we can't open the CSV file, I'm gonna get a message here that lets me know that we couldn't do that. So for that, I'm just gonna do print, and for example, I'm gonna use the info clause, and I'm gonna write error reading CSV file. And if everything goes fine, at the end, we're gonna return test data. Well, in fact, since we're not using the test data here, we're not constructing anything. Let me just maybe remove it because it's not gonna add a lot of information for us. So I'm just gonna save this. I'm gonna open the CSV file, read the necessary information, move the images to a new folder that corresponds to their labels. And with this, we will have our images in the right order. And now here, what I'm going to do is import my function. So it's order test set. And again, I'm gonna use that basically trick that I use, false, so that I deactivate parts of my code. And now we're gonna use our function that we just constructed. And remember, we're gonna have to give it the path to the images and path to the CSV. So I'm gonna do path to images, and this is going to be this one here. Control C, Control V, and let's go quickly to our path here. And also we're gonna have to give it the path to CSV. And this is going to be this one here. In fact, for the test, we can just click Shift and then copy path. And we're gonna get the full path like this. So now we have our path to the images. We also have the path to the CSV file, and then we can call our order test set function. And this function is gonna take path to images and also path to CSV. So if this function works correctly and works as it's intended to do, then now what we should have is a set of folders here that contain the right images. We're going to move these images to their corresponding folders. So everything is saved. Okay, let me run the same script again. And again, this might take a little time because we have a lot of images, but if we take a look at our folder, as you can see, it has created all of these folders, and now it's moving the images. You see their numbers going down. It's moving them to the right folder. And with this, now we have our data set in the correct format. And in fact, when we added, just a quick note here, when we added the part of replace here, it was necessary to add this part because here we have that test part as part of the image path, and if we didn't do this, it would have given us an error. And now we have our data set for the test set correctly presented, correctly ordered, and now we have a set of data or a set of folders that contain our data in a very good format that we can use for training and testing our model. And with this, we have our dataset ready. Let's see what we can do next for building our deep learning model and doing all the fun stuff for deep learning. Let's start creating our deep learning model so that we can fit our traffic science dataset that we just ordered and prepared. So for that, I'm gonna open my deep learning models file. As you remember, we have created this file where we put all of our deep learning models in it. And I'm just gonna add at the end, I'm gonna create a new function for our new deep learning model. So in the previous tutorial, I showed you for the MNIST dataset how to create a deep learning model using 3 approaches: sequential way, functional way, and by using a class that inherits from the model class. But for this example, since I have already shown you the other 3 approaches, I'm just going to use one approach, which is the functional way. So here I'm going to create a new function for my model. I'm going to call it street signs model. And what my function is going to take is the number of classes as a parameter. And now let's start building our deep learning model. So one thing to notice is that between the MNIST dataset and the science dataset, so for the science dataset, we have an RGB, RGB images. So it's you see we have blue, red, we have all colors, unlike the MNIST dataset, which was a grayscale dataset. So now we need to take this into consideration, because when you have an image that has red, blue, and green, this means it has 3 channels. If it's just different layers of grayscales, then in this case it has only 1 channel. So why I'm mentioning this? Because for our first layer here, which is the input layer, we're going to use, as before, the input layer that's imported here, and we're gonna have to give it a shape. So this shape here is gonna represent the width, height, and also the number of channels for our images. So when looking at these images, we see that most of them are almost squared shapes, and here I checked a few images just to see the size, and as you can see, this is 44 by 45, almost a square, and even the largest ones are still in squared form. And here we can see 80 by 84, almost square as well. And the same thing goes for all of the images in our dataset. So since these are small images, relatively small, and they're squared, I thought that using a size 60 by 60 would be a good choice, because I've seen some images that had width and height smaller than 60, and some of them a little higher than 60. So 60 by 60 is an acceptable choice. Although you can do something which sometimes I do, which is going through all of the images in the dataset, computing the mean of the width and the height, and maybe even the median. And by looking at those values, you can have an idea about where the widths and heights of the images in your dataset are lying. So in that case, you can basically choose a good value for your width and height and for your input model, like we're doing here. So here I'm going to choose 60 by 60. And since we have RGB images, I'm going to choose 3, which is going to be different than the first model where we had 1. And then since we have this, we're just going to do the same thing as we did for the first model for the MNIST dataset. And I'm just going to do this quickly here. So I have used the layers that we used before, which is convolution, max pooling, batch normalization, and I use them in these blocks. As you can see, these are basically similar blocks. Each time I use a convolution followed by max pool 2D, then batch normalization. And here I have actually, I wanted to show you the difference between a layer called flatten and the global average pool 2D layer. So first of all, let me import this layer here. So it's flatten, so there's no problem. And also let me get the model function from, okay, let's find them here. It should be in the, okay, I can't see it. Okay, in that case, let's just go here and do from TensorFlow.keras import model. So this is what we're going to use here. So here I have commented this part. This is the same layer that we used previously with the MNIST dataset. And I told you that you can also use the flatten layer here, which is just going to flatten all of the values that are coming from the previous layer. So in this case, the batch normalization. And what I wanted to do is to basically build this model and show it to you. And then we're gonna change this layer to global average pool 2D. And I'm gonna show you the new model. And then we're gonna look at the difference between the two. So here, basically we have our model and we can import it from here. So from deep learning models, import street signs model, and we can use it here. And just something that I also do from time to time when I'm doing experimentations such as these ones, sometimes even in my scripts that are not used in the main script. So these are scripts that just contain some utility functions and classes, just like this script here. Sometimes even in these scripts, I create basically part of my code where I can test things straight inside this script. So for example, now what I wanted to show you is this model. We're gonna build it with this layer, flatten layer, and then we're gonna build it with the global average pool 2D layer, and we're gonna see the difference there. So here I'm gonna do model equals street signs model, and for now I'm just gonna give it whatever I want, since this is not the model that I'll be using with the dataset. This is just for testing purposes. And what I want to do is to call the method summary, and this method is going to show us the model architecture, the different layers, inputs and outputs, shapes. So this is going to help us get an idea of how our model looks like. So here, let me run this Python deep learning models.py, and as you can see, the goal of this part here, this is going to help us. For example, when we're doing tests, like I'm going to show you in a minute, we can just call this script here. But if I import this script in another script, so for example, here I am importing this function from my script here. In this case, this part of the code will not be called. So this is a good way to separate parts where you just want to test something quick, and also the parts where you want to reuse them in other scripts. So with this, let me run this quickly here. And let me maybe put this like this. So this is the architecture of our deep learning model. As you can see, the input is 60 by 3, and also we have this first value here represents the batch size. So none means that it can be any batch size we want. And then there is the convolution 2D, the max pooling, and so on and so forth. And when we come at the end here, we have the flatten layer. As you can see, what the flatten layer has done is that it took all the values from the previous layer. So here we have basically some sort of a cube where you have 5 by 5, and it has a depth of 128. And what it did is that it just took all of the values and put them in one vector. That's why we get 3200, because it's equal to 5 by 5 by 128. Now, if let me change this to the global average pooling instead, and I'm going to comment this. So let me run the same script again, and also enlarge this part here. Now, when we come to the layer here, so before you see, we had the flatten layer third from the last layer. So this is, we changed it with the global average pooling 2D. And now you see we don't have 3200, because the global average pooling 2D, what it does is that it actually computes the average in these windows here. So imagine you have a cube where it's 5 by 5 by 128. So every 5 by 5 will compute the average there. So at the end, we're only left with 128 values. So this is the difference between those two layers. I wanted to show you how basically reflect in the architecture, and whether you should use one or the other. It's actually one of the things that you can experiment with. Just like I mentioned in the first tutorial, when you're doing deep learning, machine learning in general, you're going to be doing lots of experimentation. So this could be one factor of your experimentation, where you change these two different layers and see which one gives you the best results. So now we have our architecture ready, and we can call it from our main scripts here, and we can compile the model and fit the data. So we're going to be doing this next. In fact, before we compile our model and fit the data, we have to create what's called data generators. So data generators are actually going to take the images from our datasets folders. So as you remember, we have train and validation folders, and we also have the test folder that we organized. So now we're going to use some basically TensorFlow utilities that help us achieve this very easily, which is one of the main points of TensorFlow. I've been using TensorFlow for some time, and basically with every release there are lots of functionalities, new features that make your building the model, preparing the dataset, makes all of this a lot easier. So here I'm going to create a utility function. Again, I'm inside my utils.py file, which I use to add all types of utility functions that I might use in the future. So here I'm gonna define a function. I'm gonna call it create generators. And basically my function is gonna take some arguments. So the first argument is just going to be the batch size. I want to be able to pass the batch size as an argument to my generators. And also I'm gonna pass the train data path, the validation data path, and also the test data path. So as you can guess, we're gonna create generators for each part of our dataset. So the first thing we're gonna do is create a preprocessor. So let me just define it here. So this preprocessor is going to basically be used in order to preprocess our data before it's fed to our deep learning model. So for this, we're gonna use a class from TensorFlow, which is the image data generator class. So let me just import it here first. So from TensorFlow keras preprocessing image import image data generator. And here we're gonna be using this image data generator. So I'm gonna call my class here. And here, in fact, if you look at this class, image data generator, you're gonna see that you have many different transformations that you can apply. For now, let's just not worry too much about them. For now, I just want to focus on one thing, which is the rescale parameter. And the rescale parameter is gonna basically rescale our data. So it's gonna rescale our images. And here what I want to do is choose a value that will be multiplied with our data set so that it's rescale. So I want basically to divide the values of my pixels by 255, which is the maximum possible value in RGB images. So here I'm just gonna choose 1 over 255. And what this means is that I want my preprocessor to be used. I'll show you in a minute how we're gonna use it, but I want it to be used to preprocess my images before they are passed through my deep learning model. So here I'm gonna create my generators. So I need 3 generators. So train generator is going to be the first one. And for this, I'm just gonna use my preprocessor. And I'm going to use a utility function called flow from directory. So this is a very helpful function that you can use. And in fact, what it does is that it takes a path to your folder. So for example, for the train data, we're going to do train data path. So train data path. And then what it's going to do is just going to look at our folder. So for example, for the train data path folder, and it's just going to look at all the folders that exist within that directory. And it's going to suppose that each folder contains images that belong to one class, so that specific class. So this means that our generator is going to automatically know that all of the images that exist inside this folder belong to the same class. Same thing for this folder and for the other folders as well. So this is going to help us immensely. We don't need to specifically build a data set where we say this image has this label. In fact, with this utility function, TensorFlow is going to help us do that automatically. So other parameters that we need to give to this utility function is the class mode. So for the class mode, I'm going to use categorical. And for the target size, I'm going to use 60 by 60. So this means that I want all of my images to be resized to 60 by 60. And for the categorical, as I mentioned it in the first tutorial, if we use categorical here, we have to also use categorical cross entropy when we are compiling our model. We can also use sparse. Let me just check here if it's maybe shown here, class mode. It's either categorical binary or sparse. So if we use sparse, then we need to use sparse labels. If we choose categorical, then this means that our labels need to be one-hot encoded. So let's look at the next parameter. So here we're going to choose color mode to be RGB because my images are colored images. Also, there is a parameter called shuffle that I want to set to true. This means that in each epoch or in each batch, my images will be shuffled so that between two epochs, basically the order of the images will not be the same. This kind of randomness helps our model be more generalized and learn features and ignore that order between the images because we don't want our model to learn that. And finally, the batch size, we're gonna give it the batch size, which we are passing here as a parameter. So this will be for the train generator, and we're gonna be doing exactly the same thing for the validation set and for the test set. The only thing that's going to change is the path, and maybe for the test set we can set this to false because we don't need to shuffle the data when we're just testing. So let me do this quickly now. So I have finished creating generators for my different folders. So for the test data, I'm using this approach, the same thing for the validation set and for the test set. And as I mentioned, the only difference is that for the validation set, of course, I'm using the validation images. For the test set, the test images, and I'm just returning these generators here. I also set shuffle to false for validation and for test because it doesn't matter that much for when we're validating on or when we're testing our model whether we have that basically a randomness or not. That randomness matters much more when we're doing the training, which is why we're setting shuffle to true for the train generator. So now we have our generators ready. What we need to do now is to use our function so that we have our dataset ready in order to start training our deep learning model. So let's instantiate first our generators. And here, let me just maybe deactivate this part of my code because I don't need it. Of course, you don't have to always follow what I'm doing here. You can just remove these parts because we don't need them anymore. So if we split the data, we ordered the test set, so we don't need these parts. But for now, I'm just going to keep them. I might delete them next, but they will not have any effect on what we're going to add here. So first, I need to import my function that creates generators, and then I have to set the paths to my train and validation folders, so they will be these folders here. So let me just put this here. In fact, let's just delete these. They're just gonna be taking some space. And here, since I have the train folder, the validation folder, I only need to add the path to test. And here, I'm just gonna maybe change the name so that, because we're not gonna be saving anything in these folders. And here, I'm gonna set it to my test folder. So my test folder is this one. So I'm gonna copy this path, paste it, then I'm just gonna add my backward slashes here. So now we have all of our 3 paths, and I can use my create generators function, and it's going to take a batch size. Let me maybe set a batch size here. So I'm going to choose a batch size of 64. Now this is also again another parameter you can play with. You can choose different values. I recommend you choose something like a multiplied number of 2. So you would choose, for example, 2, 4, 8, 16, 32, 64, so on and so forth. And here I'm gonna keep it 64. And you might face a problem sometime when the batch size is too large. For example, let's say you choose 512. Maybe the training will not start and you're gonna get an error where it says OOM, which means out of memory, which means that you don't have enough memory to load all of those images at once. So if you face that error, I suggest you decrease this number here and it should work fine. So let's go here and pass our parameters. So path to train, path to val, and path to test. And of course, let's go to our function just to check. We're gonna get these as outputs. So let me maybe just copy them so that we can go quickly here. So now with this, I can generate I can create my generators using the images that exist in these paths here. And with this, we can now pass these generators to our deep learning model so that we can train the model. First, we're gonna create our deep learning model architecture. So for that, we're gonna use our street signs model here, street signs model, and the street signs model takes the number of classes as a parameter. So here, for the number of classes, we can actually get them using the generators, any of the generators, since the train generator is the one that contains the most images. Let me maybe just use it. So number classes equals train generator dot num classes. And then I can pass this to my deep learning model. And now I have my model ready. Then we need to do the same as we did in the first tutorial. So here we're gonna first compile our model. And to compile it, we have several options. The first one is the optimizer. So for now, let's just keep Adam as the first tutorial. Second, we need to set the loss. And here I'm gonna use categorical cross entropy. And again, I'm using categorical cross entropy because my generators here, I have set the class mode to categorical. If I set this to sparse and I set this to, and I keep this categorical, then I'm gonna have an error at the end. And the final thing we need to define here are the metrics. And for that, I'm just gonna use the accuracy. So by doing this, we're gonna have our model compiled, and what's gonna be left now is to fit the data. So here I'm gonna do model.fit. And here we can actually do something that looks a little different than the first tutorial. So in the first tutorial, we had that X and Y, but in fact, you can just pass the full generator. So this generator and this one, they all contain the correct image and also its corresponding label. We didn't have to explicitly do that by when we use the from flow from directory method, it has done this for us. So we have our generators ready. So we can just pass the train generator as a parameter like this. And then we can set, for example, other parameters like the epochs. So here we can choose whatever epochs we want. Maybe I'm just gonna add it here so that it's easily changed later. Epochs. And also we have the batch size. We're gonna use the same batch size. And also we gonna pass the validation images and the validation generator here. So for that, we can use the validation data parameter, and we can pass the val generator as the argument. So here, as you can see, we didn't have to specifically mention the images and their labels separately like we did in the MNIST example. So here in the MNIST, we had the X train contains the images, the Y train contains the labels. But in this case here, we didn't need to do that because our generator takes care of that. There's already the images and their corresponding labels. So with this, we can fit our data and we can train our deep learning model. And this would be almost identical to what we did before, apart from the generators. And I mentioned in the previous tutorial that there are some things that we need to do when we're building a project like this. So for example, one of the important things would be to save your model, save the best model during training. So I'm going to show you how to do this now. So in order to save the best model during training, we're going to use something in TensorFlow that's called callbacks. And these callbacks are actually functions that are called during the training, and basically they do whatever you want them to do. Specifically, we want to save the best model, so we're going to use a callback that saves the best model. So in order to do that, we're going to be using some modules or some classes from TensorFlow. So here I'm going to do from TensorFlow.keras.callbacks. I'm going to import a callback called model checkpoint. So here I'm going to use this one. Here I'm going to give it a name. So for example, we can call it checkpoint saver. So KPT saver. And I'm going to instantiate that class. So model checkpoint. And then I'm going to pass a set of parameters to my class. So here, the first thing we need to give it is a path to where we want our model to be saved. So path to save model. And let me maybe define it right here. So path to save model. And I just want to save it in the same directory. I want to create a directory called data, and or maybe just models, and that would be it. So I'm gonna be saving my model inside a directory here that will be called models, and then I need to give other parameters to my callback. So one thing would be the monitor, and here I'm gonna give it the val accuracy. So what this parameter is going to do, so this parameter here, monitor, is basically going to, well, monitor this value here. And what we want it to do is that we want it to follow this mode. So here I'm going to set it to max, which means that I want my, basically my program to save the model whenever I get a validation accuracy that is higher than the previous saved accuracy. And this is why I'm setting here max, because it's gonna be, my model is going to be looking at the validation accuracy, and whenever it gets a little higher, then it's gonna save it. If it gets lower, then we don't do anything, we keep the same model that was saved before. And why we're setting here max is specifically for the reason that I just mentioned, which is we need to basically only save the models that have higher validation accuracy. If, for example, I had here to monitor validation loss, then I would be using the min mode, because for the validation loss, the less it becomes, the better my model would become. So I only want to save my model when this validation accuracy becomes lower, hence the mode min. So for me, I want to monitor the validation accuracy. The higher it gets, the program will save it. So that's why I'm setting to validation accuracy and the mode to max. And also, there is a parameter called saved best only. I'm gonna set it to true. So I only want the best to be saved, which means that I'm only gonna have one model to be saved, which means that if I had a validation accuracy, I save a model for that validation accuracy. If a new model has better validation accuracy, then I'm gonna replace the previous model. If I set this to false, then I'm gonna keep the previous model and save the new one next to it. So for me, I just want to save the best one, so I'm gonna set this parameter to true. And also, we can choose a frequency of saving. So here I'm gonna set it to epoch. So we're only gonna look at the validation accuracy at the end of the epoch, and only then we can choose whether to save the parameter, the model or not. And finally, I'm just gonna set verbose to 1, which is just helps us for debugging purposes to see when the model has been saved or not. So now I have my callback ready, and to use this callback, what you need to do is to add a parameter here called callbacks to the fit function. And here you can give it a list of callbacks. So for now, we only have one, which is the checkpoint saver. So I'm gonna pass it here. If we had other callbacks, then we can also pass them here as part of the list. But we're not gonna do this unless, as I mentioned, we have another callback. And speaking of callbacks, I also want to show you another interesting callback that you can use, which we can also import from the callbacks module here, and it's called early stopping. So this callback here, what it does is that we can set some number of epochs that, according to this number of epochs, if my model does not improve, then I'm just gonna stop the training. So this could be useful when you're training for a large number of epochs, and maybe for, let's say, 30 or 50 epochs, your model does not improve at all. So it's better to just stop the training. So here, how to use this is almost the same way we use the model checkpoint callback. So we're gonna have to instantiate the class. So I'm gonna call it early stop, and I'm gonna use the class early stopping. I'm gonna monitor something. So here I'm gonna choose to monitor the validation accuracy, just like I did for the model checkpoint. And also I need to set the patience. So here, for example, I can set the patience to 10. So what this means is that I'm telling my my program here that if after 10 epochs my validation accuracy does not go higher, then just stop the training. So for example, I might use let's say 100 epochs, and after 10 epochs we reach certain validation accuracy, and at the 20th epoch, the validation accuracy does not go higher. So that means that the model did not improve. In that case, I'm just going to stop the training before continuing the rest of the 80 epochs. So this could be very useful in different scenarios, and we're using it here. And in order to tell our model to basically use this callback, we need to pass it as part of the list of callbacks here. So now we have our program ready, and we can fit the data to our model, and we can save the model inside a folder here called models, and we have everything ready. So with this, let us test our model. Let me clear the terminal. I'm gonna run Python. In fact, I just noticed that actually my script is called street instead of street signs. So let me just quickly modify this. So street signs example. And now let me call it, or let me call my script from here. So street signs example. So let's run this and see what we get. Hopefully we don't have any errors. So as you can see from the logs, when you're using generators, it also gives you an idea about the number of images that are being used. So since we have train, validation, and test, this is for the number of trained images, this is for the validation, this is for the test, and we also have 43 classes. And as you can see, the training has started and our script is working properly. So now this might take some time since it's 15 epochs. I'm gonna wait for it until it finishes, and then we're gonna look at our saved model. And maybe I'm gonna come back before it even finishes just to show you that there was a model saved here after the first epoch. So here, after the end of the first epoch, as you can see, we reached this validation accuracy. But the most important part for us now is that there's this line here that says validation accuracy improved from -infinity to 0.4. So this means that our validation accuracy has improved. This means that we're going to save the model to this folder here. And as you can see, this folder was automatically created. And if we go inside of it, we see these files here. And these files actually represent our model. So we have this file, we have these two folders. So this folder contains the weights, and all of the elements that exist inside this folder represent our model. So now each time it's improved, it's going to be saved in the same place here. And for now, I'm just going to wait until the training is done, and then I'll show you how to use that final model to evaluate the test set, for example, and to do other things. So now the training has finished. It didn't take that long. And at the end, you see that in different epochs, whenever the validation accuracy became higher, we saved the model. So now we're sure that this folder here contains the best model that was saved during the training. And now that we have this, we can use our model in order to evaluate the data sets. And this could be done easily using also some TensorFlow utilities. So for example, since we don't need this part here, I can just, for example, set this. This is also something that sometimes I do, which is to basically set what I call switchers. So train, I'm gonna set it to false because I'm not training. And I would do this whenever I'm doing part of the code that I know I might use it again. So I set it to this switcher here, and I can set it to true or false depending on what I want. And for example, I can set this test to true, and then my part of the code that does the testing will be added here. So if test, then if I am using this switch, then I want to use my model that was saved in order to evaluate my data set. So now that we have our model here, we can use some TensorFlow utilities in order to load our model. So here, for example, I can call my model and load it using tf.keras. Actually, I don't think I have. Okay, import TensorFlow as tf. I did not import TensorFlow in this module here. So tf.keras.models load model, and here I can give it a path to my model. So my model is saved in this path here, so whenever I call my script, it's going to find it. It's right next to it. And then what I can do is, for example, maybe I can basically print my model's architecture. And the most important thing is that we can use the model to evaluate the sets that we have. So I want to evaluate my model on the validation set and on the test set. So we can also do this very easily here by passing the generator directly. And maybe I can add a print here, evaluating validation set, and evaluating test set. And here I'm going to call model.evaluate on my test generator. So now if we run the code, the training will not start. We will only have the data basically loaded into these generators, and then we're gonna evaluate those generators. So here I'm gonna call my script again. Everything is saved. Let's see if this runs without any problems. Okay, again, since we have the generators, it's gonna show us this. Oh no, this is actually a summary. Okay, let me save this. I'm gonna run the script again. Hopefully there are no more errors. Let's see. Okay, the architecture is here, and then the evaluation has started. So now it finished evaluating the validation set, which is 99% accuracy, 99.67 to be exact. And on the test set, we'll see how much it is. So on the test set, we see that we get an accuracy of 96.81%, which is not too bad. It's really good. So this means that by training our model on these images here, and by testing them on the test set that we organized, these images were never seen by our model, and it still achieved a very high accuracy of 96.81%. So now you know how to basically train your model and also how to evaluate it. Let's see what we can do next. So what I would like to show you now are maybe some things that you can do to improve the results even more, because when you're doing machine learning or deep learning, you're going to be doing lots of experimentation, and your goal will be to always improve this test accuracy. This is the most important metric for you. Of course, when you're doing a task such as classification, if you have a different task, for example, object detection, then maybe your metric will be mean average precision, for example. But here, since we have classification, we want to improve this accuracy even more if we can. So I want to show you some few techniques that you can do in order to try to improve the results. The first ones are just by basically doing lots of experimentation by changing these values here. So for example, you can train for longer. I've only used 15 epochs. Maybe you can go longer, 30, 50, even 100 epochs, and see if that can improve the model. You can change the batch size. You can also change your deep learning model architecture. You can add few layers, remove few layers. You can change these numbers of filters here. You can, for example, experiment with global average pooling. You can maybe remove this and add flatten layer instead and see how all of this can affect your results. So as you can see, you have a lot of things that you can experiment with. And also, this is from maybe a model perspective, but from a data perspective, you can also do a few things. So for example, here you have the generator, and we're using this image data generator class. And in fact, inside this class, you have several data augmentation techniques. So data augmentation techniques can help a lot in avoiding overfitting, and it can also give your accuracy a bit of a notch, and so that you can get maybe a few points more. And for example, if you're going to follow this path, then I want to mention something important here. So far we created only one preprocessor that we use for train, validation, and test. But this is because the only thing we're doing now is scaling. So if we're scaling the images for the train set, we need to do it for the validation set and the test set. But if you start adding other data augmentation techniques, for example, let's say, let me just check here, shift, or maybe let me just read a little bit here. What can we use? I think there's rotation range, for example, and rotation range, for example, you can choose, I think it's in degrees. So you can choose, for example, 10 degrees. This means that your images will be rotated between 10 and minus 10 degrees. You can add other things like shift, or maybe width shift range. Yeah. So this is to shift your image a little bit from left to right, just a little bit, and you can give it a small amount. For example, let's say 0.1, which means 10%. So I want like my image to be shifted 10% to the left and 10% to the right, and between these two. So it can be like 5%, 3%. This is going to be used as a range, and you can do all sorts of other data augmentation techniques. So the first thing that I want to basically emphasize here is that if you're using this as preprocessor, you shouldn't use it for validation and for the test set. And the reason for this is that the validation and test sets basically represent the sets that your model will encounter in real life. So in real life, it's not necessarily, you're not necessarily gonna have these shifts because these are synthetic augmentations. In real life, you want to test only on real images, but when you're training, you can do all sorts of these augmentation techniques. So in order to avoid this, you should always create two preprocessors. For example, you can call this train preprocessor, and you can, for example, add another one. You can call it test preprocessor. For the test preprocessor, you remove these. You only leave the scaling part because it's necessary. If you scale the train set, then you have to apply the same thing for the validation and the test sets. But then you can use this preprocessor for the training part and this for the validation and the test generators. So this is how you would do it, and this could also bring some improvements to your model. So just make sure you follow this kind of methodology when you're doing these different data augmentation things. And apart from this, as you can see, you have several things you can do. You can add more augmentation. You can change. You can even change the target size. Maybe use 40 by 40 or 80 by 80. See if that can improve the results or not. So I definitely recommend and I urge you to experiment with this and see if you can beat this accuracy, which is 96.81%. And this is gonna help you basically learn more, and it's gonna show you the power of deep learning. Sometimes just by changing a small parameter, you can get a large improvement. And then one last thing I want to show you also in terms of things you can improve. For example, here for the optimizer, I have passed it as a string because this is one possibility to do it. Another one would be to create an optimizer here, and you can use tf.keras. The optimizers, let me check. So tf optimizers, and here you can call, for example, the optimizer Adam. And this is something that you can find in the documentation. So tf keras optimizers. So the documentation can be very, very helpful when you're working with TensorFlow. They have lots of examples. They have lots of tutorials that you can use for your projects. And here, so what I wanted to show you is that if you use the Adam optimizer like this, then you have the option to pass some parameters to it. So here, if we go to the documentation, you see that you can pass the learning rate, for example, which is a very important parameter in deep learning. These parameters here, I usually don't touch, but for the learning rate, I do lots of experimentations with it because I have seen that it can have great effect on your model. So here, for example, you can add learning rate. So LR for learning rate, let's say 0.001. So this 10 to the power of -4. And then I can pass this as my parameter here, LR. Let me check just if this is the correct way to call the parameter. Yeah, learning rate. And then I can pass it here. And then you can, this is another hyperparameter for you that you can play with and see if you can improve the results. And then the way you would do it is that you can pass this optimizer here like so. So this is also something that I wanted to show you. Just for the Adam optimizer, you see you can play with the learning rate value here. And also, since we're talking about Adam optimizer, just a quick note. You see here that there is this last parameter called, or this parameter called AMS grad, and it's by default set to false. This is actually a variation of the Adam optimizer. I've read a little bit the paper that showed this technique, and they showed that in some cases, Adam actually fails to converge. And by converging, I mean it fails to basically get the loss function to go very low. And in those cases, in many of those cases, AMS grad can help. So for example, you can also, if you're using Adam for your deep learning task, and you see that the loss function is not going down, then maybe one thing you can experiment with is to set the AMS grad to true, and you can test with this variation of Adam optimizer. So as you can see, you have a lot of things that you can do, but just this set of parameters and this set of techniques that I mentioned now can help you improve the accuracy by a large margin. So when you're done training and evaluating your model, what you basically need to do at the end is to use that model in your application. It could be a web application, it could be a mobile application, or an embedded application. And for that, what you would usually do is use this standalone script that just loads your model. And for example, it takes a path to an image as a parameter, and it gives you a prediction on that image. So this is what I'm going to show you now. So let's create a new script, and I'm going to call it, for example, predictor.py. Or let me just maybe choose my predictor.py. And in this example, what I want to do is to show you how we can just load an image, load our model, and make a prediction with our model on that image. So let me maybe start here by defining this part here. And I want to basically have a path to my image. Let me call it maybe image path. And what I would like to have is some sort of a function called predict with model. And this function would take image, it would take the image path, or maybe it would take my model and image path, and it would return to me the correct prediction. So it would be something like this. So now let me define this function here, and maybe let's start defining it here, and maybe later move it to the utilities script. So define predict with model, and it's going to take model and image path. So here what I want to do is to first load that image, and then use my model to predict on that image. So the first approach I'm going to use is by using purely TensorFlow functions. So let me import TensorFlow STF here. I'm going to use my TensorFlow import here to load my image. So I'm going to use here, I'll create a variable called image tf.io.read file, and I'm going to give it my image path here. So this is a utility function that's going to help us load this image and save it inside this variable called image. And then I want to basically decode my image, tf.image.decode PNG, since all of my images are PNG images. So here I'm gonna do this, decode as PNG. So I'm gonna decode my image, and then I need to choose the number of channels. Since it's an RGB image, I'm gonna choose 3. Then what I'm gonna do is basically rescale my image. And in order to do that, I'm gonna use a utility function also. So I'm gonna do image equals tf.image.convert image dtype. And I'm gonna give it my image as a parameter here. I'm gonna choose dtype to be tf.float32. So in fact, just by doing this part of the code here, I'm reading the file, reading the image using this read file method. I'm decoding it since it's a PNG image. I'm using decode PNG, and then by using this function here convert image dtype, is gonna convert my image pixels, since now they are unsigned integers in 8 bits. It's gonna turn them into a float 32 type, and also is gonna scale them by turning the pixel values between 0 and 1 instead of 0 and 255. So without even mentioning here the scale value by saying, for example, divide by 255, this function is going to do it for us. And you can check that by going to the documentation regarding this function here. After that, I'm going to have to resize my image. So I'm going to use tf.image.resize, and I'm going to give it my image and then a list of the width and height. And here I'm choosing 60 by 60 because, as you remember, in the generators here or in the flow from directory, we are using target size 60 by 60, which means that all of our images are resized to 60 by 60. So we need to keep that same order when reading an image to pass it through our model. So here we have resized our image, and last we need to basically expand dimensions of my tensor, and here I'm going to give it my image and axis 0. So just to explain what this does, in fact, at this level here, we're going to have a shape of 60 by 60 by 3, but by doing this, by expanding the dimensions, we're going to get a shape of 1 by 60 by 60 by 3. And this is the format that our model is expecting our images to be in. So let me check here. As you can see, the input layer expects none, then 60 by 60 by 3. And this none can be anything, but there needs to be this dimension here. So if we're using one image to pass it through our model, we need to set that first value to 1 to say that this is one image of size 60 by 60 by 3, and then our input layer will not complain because this basically follows the same shape that we defined during the training. And then once we have our image ready, what we can do is call our model predict function, and we're gonna pass the image to it. So this is gonna give us a list of probabilities of that image belonging to one of the classes. So here I'm gonna save my predictions to this variable here. So you can choose this function to return the list of probabilities. Maybe you want to use this for maybe using some threshold to say that this is acceptable or not. So at this stage here, for example, you might get 0.005 for the first class, 0.003 for the second class. Then you might get 0.99 for the class here, the third class, and then also the rest will be 0 point something, and for the rest of the other classes as well. So this means that our model, if we get a result like this, then our model thinks that this image most likely belongs to class 3 or class 2, because our folders, as you remember, they start from 0. So we start from class 0. If we go to the third class, it's actually 2. So if we run this command and we get this list here, then this means that our model thinks that this image belongs to this class here. So what we want is basically to get only that class, and we don't want to get probabilities. At least for me, that's what I want to do, but for you, feel free to maybe return this list here and then do whatever you want with it. But for me, since I just want to return the exact class that we got, I'm gonna do predictions equals numpy dot argmax. In fact, we can give it my predictions here, and let me just import numpy as np. So what this is going to give me is the index of the max value, which is exactly what I want. So in this case, for example, it would return, let me just maybe do it in a comment here. It would give me 2, because 2 is the index of the max value 0.99. And then I'm just going to return my predictions. So now we have our function ready, and here let's choose, for example, one of the images in the test set. Let's choose this, for example, and copy as path so that we can quickly do that. I'm just going to paste it here. I'm going to add the backward slashes here quickly. And then, of course, I need to load my model. So just like we did here, we can load our model by using this command here. So the model exists in this folder called models. So we're going to be able to find it from our script myPredictor.py. We're going to pass it to our function predict with model, and then we're going to get the corresponding class. And then here I'm just going to print something like, okay, I'm going to use an f string, prediction equals prediction. So let's run our script and see what we can get. Let me clear this first. Python myPredictor.py. Let me just do one last look here. See, hopefully we have no errors. Okay, well, the first prediction was actually wrong. So this prediction, it says this is class 12, but it actually is class 2. Let's test with other images as well. So here, for example, I added this image here from the test set, which should give us the label 0. So let's run our predictor.py. And here, as you can see, we get the correct result is 0. I know that the correct result is 0 because I'm just looking at the corresponding folder here. So we got the wrong result for this one, the correct one for this one. But this is basically, this is not a way to test the model. The best way to test the model is by doing evaluation as we did before. But this is just to show you how you would use your deep learning model to predict on images in a standalone application. So as you can see here, we have an application. This could be easily embedded in any sort of application, web app or mobile app or whatever. And basically, we just have a function that reads the image, uses the model, and makes prediction with it. And then you get that prediction and you can do whatever you want with it. So now you have seen how to use your model in a standalone application in order to make predictions on specific images. So just a quick recap of what we've seen in this last part. So basically we used a German traffic science dataset that was collected, and we had real life images. We explored that dataset. We prepared the training, validation, and test sets. We built a neural network the functional way. We also created data generators, and we added callbacks to our fit method. We trained and evaluated our model, and we discussed some potential improvements that we can do to get better results, for example, data augmentation. We also finished that part by running inference on single images and building standalone examples on how you would use your model. So if you have any questions regarding what we have covered so far, then please feel free to contact me on my social media accounts. So I have a LinkedIn account and also a Twitter account. And if you're interested in a free machine learning job ready checklist, which is a checklist that I put together based on my experience working on machine learning projects in the computer vision industry, then please check the link below. There will be only one link, but it's going to point you to all the necessary information regarding my social media accounts and also this free checklist.